Welcome to our first lesson for our differentiation chapter. Now, do you know what the hardest mountain to climb in the world is? If you're thinking Mount Everest, guess again. It is actually K2, which is on the China and Pakistan border. Now, the reason why it is the most difficult is firstly, the weather conditions are pretty harsh, but also it is very, very steep. In this lesson, we'll be looking at the graph of a derivative function. So in simple terms, how the slope of a graph changes over time in the x-axis. Maybe this will help any budding rock climbers out there. So in this lesson, as I said, we'll be looking at graphs of the derivative, which focuses on the study design dot point. So deducing the graph of the derivative function from the graph of a given function. And we won't be looking at the graph of a antiderivative. We'll be looking at that in another chapter. So the main thing you need to know for the graph of a derivative function of a polynomial is that the derivative function will always be 1 degree lower than your original function. We have some important key features that we need to be looking for when sketching our derivative graph. The first one is the stationary points. So the vertical axis actually tells us what our gradient is going to be. So along our normal y-axis, down here, when it crosses the x-axis, that means we have a gradient of 0. So any stationary points, for example, this one here, the gradient there is going to be 0. So when we're sketching the graph of the derivative, it's actually going to become an x-axis intercept. What we need to look out for next is any areas of positive or negative gradient. So for this example here, we've got a parabola. On the left-hand side, we can see that the gradient is positive. So for our derivative graph, it is going to be above the x-axis. And then on the right-hand side from 2 onwards, we have areas of negative gradient. So that is going to be below the x-axis. So if we wanted to draw the graph of the derivative for this function here, I've already put in the turning point there when x is 2. On the left-hand side is going to be above the x-axis, as I said. And then from 2 onwards, it's going to be below the x-axis as the gradient is negative. So since we're starting with a quadratic function, our derivative function is going to be a straight line or linear. So we can just connect through there and draw our straight line. Now, when you are drawing your derivative graphs, you're not actually expected to know what the intercept here is or the exact degree of the slope. So as long as it's painting a roughly accurate picture of what is happening with the gradient, that should be fine. Our second example here, we have a cubic graph. Again, the first thing we need to do is put in our stationary points. So we have a stationary point here when x is 0. So I'm just going to put that on the x-axis there. And our next stationary point is when x is 2. So again, I'm just going to put a dot there when x is 2. Now I'm looking for areas of positive gradient. So from here onwards, so from negative infinity up to 0, but not including 0, our gradient is positive. And then from 2 onwards, so 2 to infinity, we also have positive gradient. And then in between 0 and 2, our graph is going downwards, so we have negative gradient here. So since we started with a cubic, that means the graph of our derivative function is going to be a quadratic. The first thing I like to do is join in where the gradient is negative to form part of my parabola, so between 0 and 2 here. And then since the rest of the graph has positive gradient, I'm just going to extend that upwards so that I have my parabola shape. And just to quickly recap, the derivative is the rate of change of a function with respect to a certain variable. In our examples here, it is with respect to x. And the stationary point is a point on the graph in which the gradient is equal to 0. So for our first example, we are going to be sketching the derivative graph of this function here. Now we have a quartic function. So this is x to the power of 4. I'm not exactly sure on the rule here, but we know that the derivative graph is going to be 1 degree lower. So that means we're going to have a cubic graph. Again, first step is to find where our stationary points are, and that is here at 0 and then at 2. So we're going to mark in those on the x-axis, and then we're going to find our sections of positive and negative gradient. So from negative 2 to the left, we have a positive gradient because our graph is increasing there. From negative 2 to 0, we can see that our graph is going downwards, so it's decreasing. So from here to here, it is negative gradient. From 0 to 2, again, our graph is increasing, so we have positive gradient. And then from positive 2 onwards, our graph is decreasing, so we have negative gradient there. Now what we're going to do is fill in the general shape of our cubic here. So As we know, from -2 to 0, we have negative gradient. So that means from this point to 0, our graph should be below the x-axis. And then from 0 to 2, we have positive gradient. So it needs to be above the x-axis. From 2 onwards, it is a negative gradient. So we continue that line downwards. And then on the left-hand side there, from -infinity to -2, we have positive gradient. So we can extend that line upwards. Our last few examples have been sketching graphs of polynomial functions. But what if we don't have a polynomial? So for example, our graph here is a truncus, so y equals 1 over x squared. You can see here we don't have any turning points that we can identify. So what we need to do is look at what the gradient is doing along the x-axis. So firstly, from the left-hand side, it's almost a straight line. It is almost horizontal, meaning that the gradient is nearly 0, but not 0. From -2, we can see it starts to increase slightly. And then after -1, it tapers off quite quickly and increases quite quickly. So we are going to sketch our graph using that information that we know. So since our y-axis here is now our gradient, our line from the negative x-axis side is going to be quite close to that x-axis. And what we'll notice is it's actually going to take the shape of the graph that we have here already. On the right-hand side, we can see our graph is actually decreasing. So we have an area of negative gradient. So since our gradient is decreasing quite rapidly, it is going to be quite close to the normal y-axis, but underneath the x-axis. As it gets towards +2, it is tapering off, so it's becoming closer to 0. So that means our line is going to become closer to the x-axis, but again, it's not going to touch because it's not going to get to 0. And what we see is we actually have the graph of a rectangular hyperbola. So we have the y equals 1 over x as our gradient graph. Here's a tricky one for you. What if it's not a polynomial? What if it's not a normal graph? But if it's a hybrid or piecewise graph? What we're going to have to look at is this graph in each of its sections and look at what the gradient is doing in each section. So starting with the green, we can see that it is a positive gradient. So that means it's going to be on the positive y-axis there. The blue is part of a quadratic or a parabola. So we're going to have 2 different types of gradients there. The orange is, again, positive gradient. So it's going to be above the x-axis there. And then the purple line, we can see it has a negative slope. So it's actually going to be below the x-axis. So let's start with the green one. It is probably close to a gradient of 1. But since we weren't given any y values there, we just have to make assumptions. So for our quadratic, we have a turning point here at 1. On the left there, we have a section of negative gradient as it is decreasing. And on the right, we have a section of positive gradient. So first thing we need to do is mark in where our 0 gradient is. So I'm just putting a little dot there. And I'll also mark in where the graph is stopping. So it's stopping at 2 and it's positive up until that point. And it's also stopping at -1 and it is negative around there. And then we just join those points there. Now you'll notice that I have open-ended circles there on my straight lines. The reason for that being is because our green line and our blue line connect. However, we can't actually differentiate at that point because our 2 lines are very different. At the join there between the green and the blue, the line is not smooth, so we can't actually differentiate, which is why I have the open circles there, so not including those points. We'll have a similar issue with the orange line here. Again, it's going to connect that parabola or the quadratic line. And as we said earlier, this line has a positive gradient, so it's going to be above the x-axis there. It is steeper than the green line, so I'm going to put the straight line just a little bit above the green line on that left-hand side. And it's going from 2 till about 3. Now for our purple line, we said earlier that this has a negative gradient, so that is going to be below the x-axis. It's quite a slow decline, so it's going to be sort of near the x-axis. And I've just put it at roughly -0.5. Again, we can't tell the exact slope as we don't have our y values there. So estimation is okay there. So you can see between the orange and the purple line there, the graph does not continue. We've got a bit of a break there. So even though I have a colored in circle for the purple line, since they share an x coordinate, we cannot include the gradient at that point. So in summary, when we are sketching the derivative graph, we need to remember that our y-axis is no longer the y-axis. It becomes our gradient. So we can say it's dy dx. Along the x-axis there, we have our gradient of 0, so we need to mark in any points of 0 gradient. So for example, this one here, our gradient is 0 at 2. And then we need to work out where our gradient is positive and negative and mark that on the graph. So above the x-axis is positive gradient, below the x-axis is negative gradient. So what we're looking at next is differentiating polynomials, so x to the power of n. We'll see you then. It can be a little daunting starting this topic and being exposed to a lot of different language. So what I've done is I've created a synonym mountain full of terms that you will be using over this chapter throughout your differentiation topic. So previously you would know the gradient as m from our equation of straight lines, so y equals mx plus c. You also know it as rise over run, or the change in y over the change in x. We'll also be referring to it as the derivative, or the rate of change, or the instantaneous rate of change, or the average rate of change, or even f-x or dy dx. So there's quite a few different terms there. So keep this in the back of your mind so that you know when we're talking about the gradient or the slope or f of x, f-x, the derivative, the slope, it all means the same thing. For our second lesson, we'll be looking at differentiating functions with x to the power of n. So in this lesson, firstly, we'll be looking at differentiating x to the power of n when n is positive, and then we'll be looking at differentiating it when x is negative. So the key takeaway here when we are differentiating a polynomial, so x to the power of n, is the n comes to the front there and multiplies by our x, and then we just subtract 1 from the power. So if there's a coefficient in front of the x, what we need to do is multiply n by that coefficient first. So for example, if we have a function that's f of x equals 3x to the power of 3. In order to differentiate this, first we do f-x. We bring that power to the front, so we've got 3 times the coefficient there, x, and then we take away 1 from that power there. So we end up getting 9x squared. So we have a few differentiation rules here. The first, which I have just gone through. So if we have a coefficient there in front of x, all we need to do is multiply our derivative by that coefficient there. So we'll end up with k times the derivative, so f-x. If we have two functions that are added together, so a sum of functions, then we just differentiate them separately and add them together. Likewise, with difference of functions, we just differentiate them and then subtract them. So pretty straightforward there. And finally, if we have a function that is just a constant, we will have no gradient there. So the derivative will just be 0. So for example, if we had f of x equals 2, then the gradient is going to be 0. So a key thing here is since we are differentiating with respect to x, this one here doesn't have an x in there, so we can't differentiate. So that's why it's going to be 0. Now we've got a few different types of notation here. So the first one is our function notation. So if we're starting with f of x or g of x, then we will end up with f-x, which represents the derivative. So this part here tells us that is the derivative. The next one here, I'm not sure how to pronounce it properly, so I'm not going to attempt it. But if we have just y equals something, then we end up with dy dx. If we have, for example, y equals 2t, and we want to differentiate something like that, then the notation would be dy dt. So we just need to make sure what variables we are looking at and represent them there in the derivative properly. The last one there is operator notation. So if we just have an expression that we want to differentiate, we're just going to put d dx and then the expression in brackets there. So for example, if I want to differentiate 2x to the power of 3, then all I need to do is write d dx and then put my expression in the brackets there, write equals, and then figure out what the derivative is. So in this case, we bring the 3 to the front, multiply by the 2, so I get 6. I write my x, and then I subtract 1 from the power there. So the power was 3, so it becomes 2. And just to quickly recap, we have some vocab on the right-hand side there. So firstly, the derivative, which is what we're looking for. So again, the rate of change of a function with respect to a certain variable. And the next one is differentiation. So that is the actual process of finding the derivative of a function. So we have a few work examples that are going to go through the skills that we just worked on previously. So for the first one, we have just a normal polynomial here. So we've got y equals negative 2x to the power of 3 plus 2x squared, take away 7x plus 2. So in order to differentiate this one, we are going to write dy dx. And then again, we're going to bring that index to the front. So we have 3 times negative 2. and then take away 1 from that index. So 3 take away 1 gives us 2. The next term we have 2x squared. So the 2 comes to the front there, and taking away 1 from that index there. So 2 take away 1 becomes 1. The next term here we have negative 7x. So what we can actually think about negative 7x as, negative 7x is the same as negative 7x to the power of 1. So using what we have done just then is we bring the power to the front there. So 1 times negative 7. And then we take away 1 from that one. So we end up getting 0. Now, if you know your index laws, anything to the power of 0 becomes 1. So if we've got x to the power of 0, that becomes 1. So this one here will simplify just to negative 7. So from here on out, if we have a term that is just x to the power of 1, we can just ignore the x and just take the coefficient of that one. So finishing off this derivative here, we're just going to put that negative 7 there on the end and then simplify. So now we have 3 times negative 2, that gives us negative 6, x squared. 2 times 2 gives us 4, so plus 4x. I'm not going to write to the power of 1 because we know it's just to the power of 1. And then take away 7 on the end. So that is done for that one. For b, we have a bit of a different one. We've got a fraction there. So we've got 2x squared, take away 3x, divided by 4x. Now, in order to differentiate this one, we need to actually simplify it first. So I'm going to do that on the right-hand side, so I've got enough space to write my answer. What I can see here is that each of the terms have an x in there, so I'm going to divide through by x, and that's going to simplify to 2x, take away 3, all over 4. Now, to be able to differentiate this nicely, I'm just going to split that fraction so we have 2 terms there. So we end up getting 2x over 4, take away 3 on 4, and then we know 2 quarters is 1/2. So we end up getting x on 2, take away 3 quarters. Now we can differentiate that. So f of x is actually equal to x on 2, take 3 on 4, and now I can differentiate. So using my function notation, I write f dash x. The coefficient of x there is actually 1/2. The negative 3 quarters, there's no x there, so I'm going to ignore it. So the derivative of this graph here, or this function, is just 1/2. For c, we just have an expression, so we're using that last operator notation. So we write d dx, we write our expression in the middle, and then we differentiate like we would. So we bring the 5 to the front, and then take away 1 from that index there, or that power. So that becomes the power of 4. The next term, we've got negative 2x to the power of 4. So we bring that 4 to the front, multiply by the negative 2, and then subtract 1 from that index or power. And then lastly, we're just going to simplify that. So we've got 5 times 3, so 15, and that's x to the power of 4. 4 times negative 2 gives us negative 8. So take away 8, x to the power of 3. So for the last worked example, we looked at just finding the derivative, but now we're actually going to find what the derivative is at a certain point. So for this polynomial here, we've got f of x is negative 2x cubed plus 3x squared, take away 4. The first thing we're going to do is differentiate. So we just want to find f dash x. So again, we bring that power to the front there. So we've got 3 times negative 2x, and then take away 1 from that power. So 3 take 1 is 2. Next, we've got power of 2 here. So we're going to bring that to the front. So I've got 2 times 3x, take away 1 from that power there. So it's 1. I'm not going to write it there though. And lastly, we have our constant term. So again, there's no x there. I'm going to ignore it. Simplifying that, we get negative 6x squared plus 6x. What we need to do now is we need to sub in x equals negative 1 to find what the gradient is at that point. So I'm going to write that in my notation there and replace all the x's with negative 1. And I like to keep brackets just so that I can make sure that I'm not forgetting about that negative there. So simplifying this one, I get negative 6 times negative 1 squared. So that just becomes negative 6 times positive 1. And then I've got 6 times negative 1, so that actually gives me negative 6. So negative 6 take away negative 6 gives me negative 12. So that's telling me that the gradient when x equals negative 1 is negative 12. So it is decreasing at that point. For our second example, again, we're going to differentiate, but we want to find what the gradient is doing when x equals 1 instead of negative 1. So we already have the derivative there. So we had the negative 6x squared plus 6x. Now we're going to replace x with 1. So we end up getting negative 6 times 1 squared plus 6 times 1. So we get negative 6 plus 6, which equals 0. So since it equals 0, that actually tells us we have a stationary point there when x equals 1. For our last example, we are looking for when our gradient is equal to 0. We've already found 1, but there might be another. So what we need to do is write our gradient function down. So we have negative 6x squared plus 6x, and let that equal 0 and solve for x. So the first thing we can do is factorize. So we can see that 6 and x is common in both of those terms. So I'm going to take that out as a common factor. When I do that, I'm left with negative x here for my first term. And then for this second term, I'm left with just 1. So now what I can say is I have 6x equals 0 and negative x plus 1 also equals 0. So simplifying, we end up getting x equals 0. And as we knew before, x equals 1. For this worked example, we are finding the equation of the tangent to the curve with this rule here when x equals negative 1. So since we're looking for the equation of a tangent, we're looking for something with y equals mx plus c. We need to find what m is, and we need to find what c is. So firstly, finding m, finding the gradient, we need to differentiate. So starting that off, we write f dash x and differentiate this function here. So we bring this 2 to the front there, so we get 2x, and then ignore that x there, so we get 2x plus 3. What we need to do now is find the gradient when x equals negative 1. So we're going to substitute that into our function there. So we end up getting 2 times negative 1 plus 3. So we get negative 2 plus 3, and we get 1. So that tells us that the gradient is 1 when x equals negative 1. So we've got part of our straight line equation there. Now we need to find what c is. In order to do that, we actually need to find what the y value is when x equals 1. Otherwise, we don't have enough information. So what I'm going to do is for f of x, I'm going to find f when x equals negative 1. So I end up getting negative 1 squared plus 3 times negative 1 take away 4. So simplifying that, we get 1, take 3, take 4, and I get negative 6. So now we have found the coordinate there when the gradient equals 1. So our coordinate is negative 1, negative 6. And we're going to use that information to find our straight line equation. So we can either use this equation here, or we can use a point gradient formula. I might do both so you can see which one you would like to use best. So using y equals mx plus c, we can replace m with what we found, which is 1, and replace y with negative 6 and x with negative 1. So we get negative 6 equals negative 1 plus c. To solve for c, we need to move this negative 1 to the other side. So we're going to plus 1 on both sides. So that gives us c equals negative 5. So our equation is going to be y equals x take away 5. I'm just going to show you this using the point gradient formula. Sometimes it's less steps, so it might be handy for you to know. So our point gradient formula is y take away y1 equals m times x take away x1. What we do is replace the m again with our gradient, which we know, and then replace x1 and y1 with the coordinate that we were given. So doing that, we get y take away negative 6. So we'll end up adding 6 equals 1 times x take away negative 1. Simplifying that, we get y plus 6 equals 1 times x plus 1. We're going to expand and then move that 6 to the right-hand side. So we get y plus 6 equals just x plus 1 because it's multiplied by 1. And then we're going to take away that 6 from both sides. So we end up getting y equals x take away 5. So we've looked at differentiating x to the power of n when n is positive. Now we're going to be looking at when n is negative. So we actually use the same rule here. So we bring that power to the front and then subtract 1 from it. The key thing here is to remember that when we're dealing with a negative number, it becomes more negative. So if we have the negative 2 here, again, it comes to the front there. And then subtracting 1 from negative 2, we get negative 3. A common thing that happens is that students might write to the power of negative 1 when they finish their answer, thinking that they have subtracted 1 properly. But again, with our negatives, if we're subtracting, it becomes more negative. So just make sure that you take extra care with that one. Another point I'd like to make is that if we have something like 1 over x, it is actually the same as x to the power of negative 1. We can make sense of that using scientific notation. So you would have seen something like this before. So say, for example, we've got 3 times 10 to the power of negative 1. What that's telling us to do is move the decimal place backwards by 1. So moving that back by 1 is going to make our number smaller. So we get 0.3. which is the same as 3 over 10. If we have 3 times 10 to the negative 2, we're bringing it back 2 spaces. So that decimal place moves 2 spaces. So we get a smaller number again, 0.03, which is the same as 3 over 100 or 3 over 10 squared. So if you see something like 2 over x squared, it can be rewritten as 2 times x to the power of negative 2. So we're going to practice what we've just learnt with these two worked examples. So the very first step is we need to change these terms here so that we are dealing with just negative indices instead. So rewriting this one, we get y equals negative 4x to the power of negative 3 plus x squared. That one's fine. And then this 7 over x becomes 7 to the power of negative 1. So differentiating this, we write dy dx equals, we bring this negative 3 to the front, so we get negative 3 times negative 4, and then subtracting 1 from that power. So negative 3 take away 1 becomes negative 4. The next one here we have x squared, so that just becomes 2x. The next term we have negative 7x to the power of negative 1, so we bring that negative 1 to the front. We multiply that by the negative 7, put the x there, and then we subtract 1 from that power there. So we have negative 1, take away 1 becomes negative 2. Again, this 5 is just a constant, so there's no gradient there, so we're going to drop it off. Simplifying, we get negative 3 times negative 4 becomes positive 12, x to the power of negative 4 plus 2x is just the same. And then we have negative 1 times negative 7, so plus 7x to the negative 2. You could leave your answer like that, or you could change it so that they have positive indices. Doing that, we're going to firstly look at this term, the 12x to the power of negative 4. The 12 stays at the top of the fraction, so the numerator. And then we're going to divide by x to the power of positive 4 now. Again, the 2x stays the same. And for this last term here, the 7 goes on the top there. And we divide by x to the power of 2. For our second example, we are going to have to simplify this similar to what we've done previously. So first thing I'd like to do is just split this fraction so we have two different terms to deal with. So we get 2x to the power of 3 divided by 4x to the power of 5, and then take away 8x over 4x to the power of 5. So what we'll do now is simplify. So I've got 2 divided by 4, which just becomes 1/2. And now using our index laws, we've got x cubed divided by x to the power of 5. So we'll end up with x squared on the bottom there. So we'll have 1/2 x squared on the bottom there. Now this one here, we've got 8 over 4. So this will simplify to 2. We've got x divided by x to the power of 5. So we'll actually end up with x to the power of 4 on the bottom. Now I can't differentiate like that, so I need to change these to negative indices. So what I'm going to do is write my fraction, my 1/2, and then bring that x to the power of negative 2 up to the top. I'm going to do the same to the next term there. So I've got 2 times x to the power of negative 4. And now we can differentiate. We write f dash x. Looking at our first term, we bring that negative 2 to the front. So I've got negative 2 times x and subtracting 1 from that power. So it's going to become negative 3 and still dividing that by 2. And the next term, we've got the negative 2x to the power of negative 4. So the negative 4 comes to the front and multiplies by negative 2. And then we subtract 1 from that power there. So negative 4 take away 1 becomes negative 5. So simplifying, we end up getting negative x to the power of negative 3. The negative 4 times negative 2 becomes positive 8, x to the power of negative 5. And again, if we want to change it into positive indices, so making our fractions, we can do that. We're going to leave that negative at the top there for our first term. So we'll have negative 1 as a numerator, and then x to the power of 3 as a denominator, plus, and then our 8 is going to be at the top there, over x to the power of 5. So the main thing I'd like you to take from this lesson is if we are dealing with negative indices, please make sure that when we are differentiating, the power becomes more negative. So if we start with negative 2, taking away 1 becomes negative 3. Again, we've got our synonym mountain there, so please familiarize yourself with the different terms that we're going to be using. And next up, we are going to be looking at differentiating rational powers. You've probably seen this before, but this is what happens when pi talks to I. I'm not sure what they're fighting about, but apparently they're still fighting to this day. Anyway, this is just a quick reminder of what a rational number is, because that's what we'll be dealing with in this lesson. So a rational number is something like a fraction. We've got p over q, where they are both integers, and where q is not equal to 0 because we can't divide by 0. A couple of examples of a rational number. We have a half. We could have 4 over 7. We could have negative 5,000 over 23. So this is what we mean by a rational number. So just keep that in your mind because we'll be saying rational rather than fractional. Again, in this lesson, we'll be looking at differentiating rational powers. So this is the same study design dot point that we've been covering the last few lessons. So we've got derivatives of x to the power of n, but in this case, we have n is p over q, so our rational index there. So again, we're going to be using the same rule that we have been the last few lessons. So we bring the power to the front and we take away 1 from the power. But again, our power now is a rational number. So we're going to use n over m in this case. So for this example here, we've got 2 times x to the power of a third. When we differentiate this, we bring this third to the front like we have been previously. Then we take away 1 from that power. Now this is where it might trip some people up. So when we're taking away 1 here, if you like, you could rewrite it as a fraction. So if I've got a third take away 1, it's the same as a third take away 3/3. And now we can just take away the numerators there. So 1 take away 3, we get negative 2 over 3. So that is how I've got my power there. So the answer is 2/3 x times negative 2/3. Another reminder for you, I've just put down the bottom here as a teacher's tip. If we've got something like the square root of x, a reminder that we can rewrite that as x to the power of a half. If we've got the cube root of something, so that looks like this, we rewrite that as x to the power of 1/3. So sometimes we might have something a little bit different. So we could have the cube root of x squared, or it could be written as the cube root of x and then squared. What that's going to look like as a rational power is x to the power of 2/3. So just keep these little rules in mind when you are dealing with questions like these. So putting this into practice, our first example here, we've got y equals 2x to the power of 3/2 plus 2 times the square root of x, take away 5x. The first thing we're going to have to do is change this square root of x. So as we saw from the previous video, that square root of x is the same as x to the power of a half. So I'm just going to rewrite that. So we get y equals 2x to the power of 3/2 plus 2x to the power of a half, and then take away 5x. So now we've got it into something a bit more workable. We can differentiate from here. So we write dy dx and differentiate like we normally would. So we bring this power to the front. So we have 3/2 times 2x, and then taking away 1 from that power. So we've got 3/2 take away 2/2. So that gives us 1/2. And then differentiating this second term, we've got 2x to the power of a half. So again, bring this half to the front. So the power to the front, multiply by 2x, and then take away 1 from the power. So we've got a half, taking away 1 will give us a negative half. And then our last term, so negative 5x, the gradient there is just going to be negative 5. So simplifying this, we just need to multiply all of our fractions together. So we've got 3/2 times 2. So you could just cancel those 2's out, or you could multiply 3 by 2 and then divide by 2. We'll still end up with 3 anyway. So we get 3x to the power of a half. Our next term, we've got a half times 2, so that's just going to be 1. So instead of writing 1, I'm just going to write x to the power of a negative half, and then my negative 5 at the end there. Now I could rewrite this so that all of my powers are positive, and I could rewrite them so I have the square root of x instead of to the power of a half, or I could just leave it like that. So I'll show you both ways. So firstly, it's going to be 3 times the square root of x plus 1 over the square root of x, because we've got that negative power. It's going to be to the bottom, and then take away 5 at the end. For our second example, we have f of x equals 6x squared take away 8x divided by 4 times the square root of x. The first thing we need to do is try to get rid of that denominator. So I'm going to split these fractions so that I can get it into something a bit more workable. So firstly, splitting the fraction, we get 6x squared over 4 times the square root of x, take away 8x over 4 times the square root of x. Now I'm going to rewrite these square roots to the power of a half instead. And now in order to simplify, I've got 6 divided by 4, so 2 is common there. So I'm going to divide both of them by 2. So I get 3 over 2 for that one. Now, for the x terms, I've got x squared divided by x to the power of a half. So what happens here is we take the powers away from each other. So I have 2 take away a half. So that leaves me with x to the power of 3 halves. For the next term there, I've got 8 divided by 4, which is 2. So I've got x to the power of 1 divided by x to the power of a half. So I've got 1 take away a half, leaving me with just a half. So I write 2x to the power of a half. So now I've got it into something, again, a little bit more workable, so I can differentiate from here. So to start, I write f dash x equals, and now for my first term, I bring the 3 over 2 to the front, so the power to the front. So I've got 3 halves times 3 halves. I write x, and then I take away 1 from the power there. So taking away 1 is going to leave me with 1 half. And my next term, again, I bring the power to the front, so I've got a half times 2. X, and then taking away 1 from 1 half. So that leaves me with a negative half. Simplifying this, I get 3 times 3, so 9, over 2 2's, which is 4, x to the power of a half, take away, and then I've got a half times 2, so that leaves me with just 1. I'm just going to ignore the 1 and just write x to the power of a negative half. Again, I could leave my answer like that, or I could rewrite it just so that I have positive indices. So rewriting, I'll have 9 over 4, x to the power of a half, take away 1 over x to the half. Okay, again, I could rewrite it so I have the square roots. So I've got 9 times the square root of x on 4, take away 1 on the square root of x. So there's a few different ways you could write your answer there. So find the equation of the tangent to the curve of y equals 2x to the power of a half plus 5x to the power of 2/3, take away x, when x equals 1. So the first thing we need to do, obviously, is to find the gradient, and then we're going to find what the gradient is when x equals 1. We also need to find what y is when x equals 1. So there's 2 different things you could do. It's up to you which one you want to start with. I'm just going to start with finding the gradient. So we write dy dx equals, we bring this half to the front. So we've got a half times 2x, and then take away 1 from that power. So a half take away 1 is a negative half. And for our next term, we bring this 2/3 to the front. So 2/3 times 5x, and then take away 1 from that power. So we've got 2/3 take away 1, or 2/3 take away 3/3, which gives us negative third. And our last term, the gradient there of the negative x is just going to be negative 1. Now, since we're substituting, I'm going to rewrite this using positive indices and using our square root function, just so it's a little bit easier to work with. So firstly, simplifying, I've got a half times 2, which gives me just 1. And since I've got x to the power of a negative half, that means it's going to be on the bottom. So we've got a fraction there. So I've got 1 over the square root of x. My next term, I've got 2/3 times 5. So I've got 10/3. And I've got x to the power of a negative third. So that means I've got that on the bottom there. So we'll have 3 times the cube root of x. And then lastly, we've just got take away 1 on the end. So now we've got our derivative, we need to substitute in x equals 1. So doing that gives 1 divided by the square root of 1 plus 10 over 3 times the cube root of 1, and then take away 1. So we'll end up getting 1 plus 10/3 take away 1. So our gradient there when x equals 1 is just 10/3. So now we've found our gradient, we need to find what y is when x equals 1. So we're just going to substitute 1 into our initial equation, so into y equals. So in doing that, we get 2 times 1 to the power of a half plus 5 times 1 to the power of 2/3, take away 1. Now, since we're just dealing with 1, we can easily do this because 1 to the power of anything is going to be 1. So simplifying that, we get 2 plus 5 and then take 1, which is 6. So now we've got our coordinate. So our coordinate is 1, 6. We've got our gradient of 10/3. So now we can either use a point gradient formula or just y equals mx plus c. I'm going to use the point gradient formula. So again, that is y take away y1 equals m times x take x1. And I'm going to substitute in everything that I have there. So y1 is going to be 6, m is going to be 10/3, and x1 is just 1. So now I need to expand. So I'm going to expand that right-hand side. So 10/3 times x gives me 10x on 3, and then take away 10/3. And lastly, I need to add 6 so that I just have y as the subject. So I get y equals 10x on 3, take 10/3, and then plus 6. So in order to add 6 to 10/3, I could change the 6 into thirds. So I'm just going to write that over here just so that you know. So we start with negative 10 thirds and we're adding 6 but changing into thirds. So 6 times 3 is 18. So I've got negative 10 plus 18 thirds. So that leaves me with positive 8 on 3. So then I write that down in my equation so that the equation of the tangent to this curve when x equals 1 is y equals 10x on 3 plus 8 on 3. So we have a worked example here that has been adapted from one of the VCE exams. It is from the 2016 exam 2. And what we have is we've got the graph of f of x is 2x plus 1 over x plus 2, but we've only shown part of the graph. So we've got the right-hand side of the graph. We've got this point here, P, which is CD. And we've been asked to find the exact values of C and D so that the distance of this point to the origin is a minimum. So what we mean is from here to the origin is a minimum. Now, in order to figure this out, firstly, we need to rewrite this rule in terms of C and D. So our first coordinate is just going to be C. So C is just C. And then in order to find what D equals, we're going to substitute in that point that we know. So we need to substitute in x equals C. So in our rule of f of x, we're going to define f of C. So just replacing all of those x's with a c. So now we have c and d at the moment. We're going to fix them up later. From here, we've been asked to find the minimum distance between these 2 points. And that's sort of a key word to tell you that we need to use that distance formula. So I'm just going to write that out. We've got the square root of x2 take x1 all squared plus y2 take y1 all squared as well. And what I've drawn here is just a triangle to show you why we've used that distance formula and how we can use it. So on the x-axis there, the distance there is just c. So this first bracket there is just going to be c. So we'll have c squared. The next one here, this is going to be the height, so what d is. So we can just replace this y2 take y1 with what d was. So we've got 2c plus 1 over c plus 2 all squared. Now, we're finding the minimum distance. So since it's a minimum, we are going to differentiate and let it equal 0. Now, since it's exam 2, we can use our calculator. So we'll use that next. Now, you will be learning more about minimum and how to apply this in future lessons, but I just thought this would be a nice little taster for you. So we're going to put this into our calculator and solve for the value of c for when our derivative equals 0. So now we have our calculator. What we are trying to find is when the distance is at a minimum. So we're going to use our solve function. So we click on solve and then we go to math 2 to find our derivative functions there. So I've just used the operator notation. I've put my rule in and then I've let it equal 0 and I've been given 2 answers here. Now, this is where some students tripped up because we've maybe chosen the incorrect answer or chosen 2. So because our initial graph said that we are using the right-hand side of the graph, so we don't have any values that are smaller than x equals negative 2, we're going to choose this value here. So x equals square root of 3 take away 2. That's going to be our bigger value. So if we let c equal the square root of 3 take away 2, and then we're going to find what d is using that. So to finish off, when we are differentiating using rational numbers, again, rational number being a fraction, we've got p over q. We differentiate it like we normally would, like we have been. So we bring that power to the front and take away 1 from the power. Again, making sure that we are well aware of what our index laws are and being able to change from a square root to a normal power. So in our next lesson, we'll be looking at the chain rule. So we'll see you then. Since this lesson is looking at differentiating using the chain rule, I thought it'd be nice to show you a visual of how I sort of remember differentiating functions like this. So the chain rule is used for composition of functions when we've got a function within a function. And so to me, that always reminds me of these Russian nesting dolls, how you've got something within another thing. So when we're differentiating them, we need to obviously make sure that we are differentiating the outside, but not forget about the guy on the inside because he's really important as well. Okay, so when we're differentiating constant functions, so when we've got f of either g of x, or if you know the other notation, so f of g, we've got 2 different functions here, so we need to treat them separately. Okay, so I like to think of these little Russian nesting dolls to help me remember to differentiate both of these. So again, in this lesson, we are looking at the chain rule. So this links to the study design dot point that we have here, derivatives for x to the power of n. But instead of x to the power of n, we might have something like x plus a to the power of n. So that is when we're using the chain rule. So when we're differentiating using the chain rule, again, as I said previously, we are differentiating composite functions. So here we've got h of x is a composition of f and g of x. So in order to differentiate this, we need to differentiate them separately and then put it all together. So what it looks like is this rule here, which probably doesn't mean much to you yet, but when we do an example, it will mean a little bit more. So when we are using the other notation, so dy dx, we've got two different functions that we're going to multiply together. So I'm going to go to the example first, then the rules here make a bit more sense. So for our example here, we've got y equals, in brackets, x to the power of 3 plus 2x, and then all squared. So what we're going to do is we're going to find what these two different functions are and separate them. So the little guy on the inside is this here, x cubed plus 2x. So we're going to call that u now, and then we are going to rewrite y as u. So we've got u squared. So again, what I've done is I have replaced this x cubed plus 2x with a u, and then rewritten y equals u squared. What we can do now is differentiate them separately. So we've got u is x cubed plus 2x. So differentiating that, we use our differentiation rules that we know. So we bring the 3 to the front. We've got 3 to the front there. And then taking away 1 from the power. So we get 3x squared for that first term. Differentiating the second term there, we've got just 2x. So it just becomes 2. So we have differentiated u with respect to x. Notice how the notation changes. It's not dy, it is du, because that is what the subject was. Next, we're going to differentiate u squared. So we have dy du, because it is in terms of u there. So when we're differentiating that one, the 2 comes to the front, and then we take away 1 from the power. So we just have 2u to the power of 1. From here, what we need to do is multiply these two derivatives together. So I've just put the 2u at the front there, just because it's smaller and a little bit easier to keep track of what we're doing. It doesn't really matter which position you put them, so I'm just taking note of what I've done there. So I've got the 2u at the front multiplied by the derivative of u. So this one comes over here on the right-hand side there. Then what we need to do is replace u with what we had at the top here. So we had u equals x to the power of 3 plus 2x. Now, I can't leave my answer in terms of u, which is why I've had to replace it here. So I'm going to replace it in there. So I still have 2 times u, and then multiplying by the derivative of u as well. So it looks a little bit messy, but we need to differentiate both things differently and then multiply them at the end. So don't worry, we're going to put that into practice. So we've got a couple of examples here. The first one, we're looking at y equals, in brackets, 4x plus 2, and then all squared. So a nice easy one to start with. So firstly, we're just going to identify what u equals. So it is the function on the inside of those brackets. So we've got this here, the 4x plus 2 is u. So we're just going to rewrite y in terms of u. So that means we have y equals u squared. Our next step is to differentiate each of these separately. So we've got du dx, and we just have 4x plus 2. So the derivative here, or the gradient there, is just 4. And then differentiating y with respect to u, we have dy du. We bring the 2 to the front there, so we end up with 2u. So now, putting this all together, we write dy dx, and we're going to be multiplying both of those together. So I'm just going to write what we are doing. So we have du dx times dy du, and you'll notice that the du's cancel out, so we end up with dy dx. So substituting in what we have there, du dx is equal to 4. And multiplying that by what dy du was, which was 2u. So simplifying that, we get 8u, and then replacing u with what we had at the top here. So u was 4x plus 2. So I'm going to rewrite that. So I have 8, and then in brackets 4x plus 2. You could expand those brackets if you want to. So we'll end up with 32x plus 16. Now, that's a lot of writing just for a simple question like this. So I'm going to show you a quicker way for simple questions like this one. I'm just going to write it in green so we can sort of keep track of what's happening here. So rewriting the question, we've got y equals, in brackets, 4x plus 2 all squared. And the quick way to do this is to recognize this power here and use the rule that we've been using previously. So we bring that power to the front. So I'm going to write dy dx equals 2. I write everything that's in the bracket the same as it was before. I take away 1 from the power there, so that's just the power of 1. And now where it's different is I multiply by the derivative of the inside there. So we know from the example we just did on the left-hand side here that the derivative was 4. So I'm going to multiply that by 4. Simplifying that, I get 8 times 4x plus 2. And again, you could expand it, and we know that that is going to be 32x plus 2. So it's much quicker and simpler, but I would only recommend using it for questions like this one where the question is a little bit simpler as well. For the next example, we have f of x equals negative 2 times, in brackets, 5x plus 6, and then to the power of 3. So again, identifying what u is and then rewriting your rule. So u is going to be what's in the brackets here. So we let u equal 5x plus 6. And what I'm going to do as well, instead of writing f of x, I'm just going to say let y equal f of x. So then I can use that notation instead. So then y is going to be negative 2u3. So again, just replacing what's in the bracket there with u and then rewriting my rule. So now I've got my two different functions and I can differentiate them separately. So the first one, I have du dx equals 5. So just the gradient there, the coefficient of x there. And then differentiating y, I get dy du, again in terms of u, equals, now I bring that 3 to the front, so I've got 3 times negative 2, and then taking away 1 from the power there. Simplifying that, I get negative 6u squared. Now putting that all together, we multiply these, so we write dy dx equals this one here times this one over here. So 5 times negative 6u squared, so I get negative 30u squared. And again, I can't leave my answer like this. I need to have it in terms of x. So I'm going to replace that u with what we had at the start, so the 5x plus 6. So I get negative 30, open brackets, 5x plus 6, and to the power of 2. So we've done a couple of examples using the longer way. Now for A, I'm going to use the short version. So what I can do is just write dy dx straight away, bringing that power to the front. So I get 2 times 3, and then I keep my bracket as is. So I've got 2x take away 5, taking away 1 from the power there. So it's just the power of 1. I'm going to leave it as it is. And then multiply by the derivative of the inside function there. So the derivative of 2x take away 5 is just going to be 2. So I multiply by 2. Simplifying that, I have 2 times 3. So I get 6. And then my bracket, I write as it is, times 2. I could have done that on the same line, but I'm just going to take a couple of extra steps. Now I've got 6 times 2, so 12. Then in brackets, 2x take 5. Again, I could leave it like that, or I could expand. So either way, we end up with 24x take away 60. Now for this example, we need to change this one so that we have a bracket. So hopefully you remember from your index laws that when we have a square root, it is actually to the power of a half. So rewriting this, we've got f of x equals, then open our brackets, 3x squared, take 5x, and that is to the power of a half. So now we can differentiate like normal using the chain rule. So we write f dash x, which is our notation for this one. We're going to bring that half to the front there, open our brackets, rewrite that like normal. And now we need to take away 1 from the power here. So we've got a half, taking away 1. So we end up getting a negative half. And lastly, we need to multiply by the derivative of the inside here. So we're looking at 3x squared take away 5x. So the derivative of that, I'm just going to write this over the right-hand side so you can keep track. So when we differentiate that, we end up getting 6x take away 5. So now we're going to multiply by that. So I've got multiplied by 6x take away 5. Now, please remember to keep brackets around this because we're multiplying by this whole expression, not just 6x and then take away 5 on the end. So that is a mistake I see all the time, okay? So please make sure you're keeping brackets around everything. What we can do from here is, since we have a negative index there, we're going to put that at the bottom. So we're going to create a fraction. So I'll have 1 at the top. I'm going to draw my fraction line there, and I'll have the 2 down the bottom. And then open my brackets and write what's in there. So I've got 3x squared, take 5x, and that's going to be to the power of a positive half now that it's on the bottom. And since we were multiplying by 6x take away 5, that can just go on the top there. So I'm just going to rewrite that a little bit nicer. So we end up getting 6x take away 5 divided by 2 times the square root of what's in the bracket there. So I could leave it as a power of a half, or I could change it back to a square root. So I might do that one. So we end up getting 2 times the square root of 3x squared, take 5x. For this worked example, we have g of x equals -1 divided by, and then in bracket 3x squared, take away 2x all squared. So in order to differentiate this, firstly, we're going to have to change to negative indices. So that's going to look like -1 times 3x squared, take 2x in brackets, and then to the power of -2. And what we're going to do now is we're going to use our substitution. So I'm going to say that u is equal to everything inside the bracket. So I've got 3x squared take 2x. And I'm going to say let y equal g of x, so I can be using y. So let y equal g of x. So we have y equals -u to the power of -2. So I've just replaced everything in the bracket there with u. So now I can differentiate both of those separately. So starting with u, we have du dx. That gives us 2 times 3, so 6x. And that's just going to be to the power of 1. Take away, the derivative there is just going to be 2. And then for y, we have dy du. All right, bringing that -2 to the front, we've got -2 times -u. Taking away 1 from the power, so we've got -2 take away 1 is -3. Remember, becomes more negative. And then simplifying that, we have -2 times -1, so just +2, u, -3. Now putting that all together, I'm just going to write down the bottom here, we have dy dx equals these two multiplied together, so 6x take 2. Again, remember to keep your brackets there, multiplied by 2u to the power of -3. What we can do now is rewrite our u, so bring that back in. So I've got 6x take away 2 times 2, and then rewrite u. So we've got 3x squared take 2x to the power of -3. What we can do from here is we can change this one so we have positive indices, so bring that down to the bottom, so the denominator, and then leaving our 6x take 2 and then times 2 at the top. And lastly, we can just multiply through by 2 just to make it nice and simple. So we get 12x, take away 4, and then divided by 3x squared, take 2x, all to the power of 3. And that's our answer. Okay, we have a show that question. So that means that we need to show our working out to prove that we've got 2x divided by x take away 1 equals this here. So when we have a question like this, what we need to do is we need to try and manipulate that fraction in order to get it looking something like this over here. So I'm just going to rewrite it. I've got 2x over x take away 1. What I can do is, firstly, I recognize that I've got 2x at the top. So I want to try and find something so that I can eventually take out a common factor and then cancel something out. So what I'm going to do is I'm going to take away 2 and then add 2. So I'm not actually changing the value of anything. I'm just changing what it looks like. And then divide by x take away 1. What I can do from here is split the fractions. So I'm just going to have what I want on the left-hand side and then everything else on the right-hand side. So I'm going to keep that 2x take away 2, and you'll see why in a second. And that's divided by x take away 1. And then we've just got 2 on the right-hand side over x take away 1. What you can see here now is that 2 is common in both of those terms. So I'm going to take that out as a common factor and factorize it. So I get 2 times x take away 1 in brackets divided by x take away 1, and then just rewriting the second term there. So 2 over x take away 1. What I can do now is I have x take away 1 on the top and the bottom, so I'm going to cancel those out. So that leaves me with 2 plus 2 over x take away 1, which is what we wanted in the first place. So now that I have changed it into that form, I can find its derivative now. So now that I have it into something a bit more workable, I need to differentiate this. So I'm just going to rewrite that at the top here. So I've got 2 plus 2 over x take away 1. Now, what I need to do is actually change this into negative indices so I can differentiate this. So what I have is 2 plus 2 times x take away 1 and then to the power of -1. And now I can differentiate that. So I'm going to use the operator notation. So just the d dx, open my brackets, got 2 plus 2 in brackets, x take away 1 to the power of -1. Differentiating that using the chain rule. So firstly, this 2 here, there's no x there, so I'm just going to ignore that. I'm going to use the quicker version of the chain rule. So I bring the -1 to the front there, so -1 times 2. I rewrite my bracket as normal, and then I take away 1 from the power there. So -1 take 1 becomes -2. And now I multiply by the derivative of what's on the inside of that bracket there. So it's just x take away 1, so the derivative there is 1. Now I can simplify, so I've got -1 times 2 times 1, so that gives me -2. Rewrite my bracket to power of -2. And now I could rewrite it so that I only have positive indices. So I get -2 on the top and then x take away 1 squared on the bottom. So to sum up what we did in this lesson, we've got our rule here for the chain rule. So if we have f of g of x, we differentiate f first and we keep g as normal. So keep our bracket as normal and then multiply by the derivative of what's inside the bracket. So hopefully you can make a bit more sense of what this rule is telling you now. So what's coming up next is we are differentiating e to the power of x. So I could have shown you a meme or a bad maths joke to show you the derivative of e to the x, but I didn't. You're welcome. Instead, what I'm going to do is show you why e to the x, the derivative is going to be the exact same. And we're going to use our graphing skills that we did a few lessons earlier. So looking at the left-hand side here, we can see that the gradient is almost 0. So it's just about to touch the x-axis, but it won't. So in my red pen, I'm just going to sketch what the derivative graph would look like. So it's very, very slow gradient there. And then it's starting to pick up a bit over here at -1. And then it is increasing quite rapidly once we cross the y-axis there, and then increasing exponentially. So what we notice is when we have the graph of e to the x, the derivative graph is exactly the same, but it's not always going to be the case if we have a different power. But we'll look at that shortly. Again, in this lesson, we're looking at differentiating e to the power of x. So in this lesson, we are moving on to a different section of the study design dot point. So we're looking at derivatives of e to the x. As we saw on the first slide, the derivative of e to the x, or the exponential, is the exact same. So when we have the derivative, it is e to the x. However, if we have a different power, if we've got a coefficient there of x, so e to the kx, what we need to do is use the chain rule, and what you'll see is that the coefficient is going to come in front of the e. So using the chain rule, I'll show you why that works. So if we've got y equals e to the power of kx, what we're going to do is let u equal kx, and then we have y equals e to the power of u instead. So again, using the chain rule, we differentiate them separately. So when we differentiate e to the power of u, we get the same thing. And when we differentiate u equals kx, we just get k for the derivative. Now the next step is to multiply those together. So we're multiplying e to the u times k. So we get k times e to the power of u, replacing u with kx. So we end up getting ke to the power of kx. So when we're drawing the graph of a derivative of something like this, the graph will actually change compared to what we saw on the first slide there. So I've got an example here that's y equals e to the power of 2x. So if we differentiate this one, just using the rule on the side there on the left, we bring that 2 of the 2x at the front, or differentiate 2x and we get 2. We bring that 2 to the front, so we end up getting 2e to the power of 2x. And what this graph will look like is this 2 is actually going to stretch the graph upwards, so it is a dilation. So what we're going to end up having is a similar graph, but it's going to be a bit of a steeper increase. So if we want to graph this one, firstly, I want to find what the y-intercept is going to be. In order to do that, I need to let x equal 0. So I'm going to just rewrite this. I'm going to say that I've got f of x instead of y. So in order to sketch this one, I let x equal 0. So I have 2e to the power of 2 times 0. So I end up getting 2e to the 0. Anything to the power of 0 equals 1. So that leaves me with 2 times 1, so just 2. So that is going to be my intercept there on the y-axis. So I'm just going to mark that one in. So you can see already it's a step above where the original graph was. And now I'm just going to sketch in my graph. So it's going to look very similar, but it does have a different intercept and it's going to be a little bit steeper. So you can see here how we have a different graph compared to the one that we started with at the start of the lesson. So if we have a coefficient there of x in our graph, it's going to be just a little bit different. On the right-hand side here, we have just a definition of what an exponential is. So it is a function in which the rate of change constantly increases, which is what you can see here. It starts off slowly, and then as we move towards the positive x-axis, it increases rapidly. And down the bottom there, I've just put a teacher's tip. So just the relationship between log and exponentials. We'll deal with logs in the next lesson, but I just thought I'd leave it here for you just so we can see the difference between them as they are inverses. So there is a relationship. So we've got if x equals log a of y, then we have the relationship that a to the power of x equals y as well. So we'll use those in a few worked examples shortly. And just to recap, we will need to know what our index laws are. So this should be second nature to you. So I've left this slide on here for you just as a bit of a reminder. So the first one, if we are multiplying indices that have the same base, so the base there is a, then we are going to add our indices together. Okay. The next one is if we are dividing indexes here that have the same base, we subtract these. So it'll be a to the power of m take away n. The next one, if we raise one to the power of something, so if we've got a to the power of m and then we raise it again, we are going to be multiplying those two together. So we get a to the power of m times n instead. The next one, we've looked at this in previous lessons. So if we have a negative power, we know that this actually becomes a fraction and it goes to the denominator. So if we have a to the power of negative m, it becomes 1 over a to the power of m. So on the bottom there of the fraction. As we saw previously as well, if we have any number to the power of 0, we get 1. So that's what we've got here. A to the power of 0 equals 1. And lastly, quite obviously, if we have a to the power of 1, it equals a. I've put a link on the right-hand side here as well. So this is from chapter 6, just a review of your index laws. So putting this into practice, the very first question we've got here is y equals e to the power of 3x. Nice and simple one to start with. All we have to do there is bring that 3 to the front. We know the derivative of 3x is just 3, so that's going to go to the front. So the derivative of y equals e to the 3x is going to be 3 times e to the power of 3x. The next one's a little bit trickier, so we might use the chain rule using the substitution. So what I'm going to do is I'm going to let u equal that power there. So I have u equals x squared. And then I'm going to use y, and I'm going to let y equal 2e to the power of u. So just replacing that x squared with u. Now I can differentiate them separately. So if I differentiate u, we write du dx, and we bring that 2 to the front there. So we get 2x as the derivative. For the next one, we have y equals 2e to the power of u. Differentiating this one, we write dy du, because it's in terms of u. And all we need to do here is write exactly the same thing, so 2e to the power of u. Nothing changes there. Lastly, we multiply these together. So dy dx is going to be 2x times 2e to the power of u. So we get 4xe to the power of u, and now we can replace u with what we substituted it to be. So u is going to become x squared. So we end up getting 4xe to the x squared as our derivative. And lastly, we've got a bit of a tricky one here. We've got 2e to the power of 3x take away 5, all squared. So again, we're going to use that substitution. So I'm going to let u equal 3x take away 5, all squared. And then I'm going to use y again. So I'm going to say that y equals 2e to the power of u. So again, differentiate them separately. I have du dx equals, I bring that 2 to the front. So it's sort of a chain rule within a chain rule. Bring that 2 to the front, I get 2 times 3x take away 5, and then take away 1 from that power, so just the power of 1. I can expand that or leave it like that. I might expand it. So I get 2 times 3x, so 6x, and 2 times 5, so take away 10. And now differentiating y, so we get dy du, again, because it's in terms of u. And again, nothing changes. It is still 2e to the power of u. So putting that all together, we are going to multiply both of those derivatives. So we have dy dx equals 6x take away 10 and multiplied by 2e to the power of u. So we can expand that bracket there and multiply the 2 through. So we can have 12x take away 20, and again, keeping that in brackets though. And then e to the power of u, and we're just going to rewrite u. So replace it with the 3x take away 5 all squared. So our derivative for this one is 12x take away 20e to the power of 3x take away 5 all squared. Okay, so these examples are increasing in difficulty here. So firstly, what we need to do is rewrite this using negative indices so that I can differentiate this easily. So rewriting it, we have f of x equals -1. We're going to multiply that by the e to the power of 3x, but it's going to be a -3x. And we're going to leave that 2 at the bottom because it's still 1/2. I'm just going to simplify that so I don't have 1e. So I have -e to the power of 3x instead over 2. And now we can differentiate that. So since I only have a power of -3x, I'm just going to use the quick way. So I bring the -3 to the front. So I have -3 times -e to the power of -3x and all divided by 2. Simplifying that gives 3e to the -3x all over 2. For this example here, I have y equals 2e to the power of x plus 4e to the power of 4x. Take away 1, all divided by e to the power of 3x. So what I can do is I can split the fractions so I have 3 different terms to make it a little bit easier to work with. And in doing that, I will simplify the terms there so I don't have any fractions. I'll just be dealing with negative indices or positive indices. We'll see what happens. So firstly, splitting the fraction, we get y equals 2e to the power of x over e to the power of 3x plus 4e to the power of 4x on e to the 3x, and then take 1 over e to the 3x. Now to simplify this, we are going to use the index laws that you saw previously. So we have 2e to the power of x divided by e to the 3x. So what we're going to do is subtract those powers. So I have x take away 3x. That leaves me with -2x. So I write 2e to the -2x. My next one, I have e to the 4x divided by e to the 3x. That one's nice and easy. So 4x take 3x is just x. So that leaves me with 4e to the x. And the last one, I'm just going to have a negative index. So I'm just going to bring the e to the power of 3x to the top and make it negative. So now I have something I can differentiate quite easily. So we write dy dx and differentiate. So here, the first thing I'm going to do is bring the -2 to the front and multiply by 2. All right, for the next term, it's just 4e to the power of x. So I'm just going to leave it as it is. And the last one, I have -e to the power of -3x. So I'm just going to bring that -3 to the front there as the derivative of the power. So we have -3 times -e, and that power just stays the same. There's no changing that one. And now we just need to simplify so that our answer is nice and easy to follow. So we have -2 times 2, so -4e to the -2x plus 4e to the x. That can stay as it is. And then -3 times -e, so +3e, -3x. So I could leave my answer like this, or I could rewrite it so that my indices are positive. So doing that, I'll have -4 at the top for this term, and then the e to the 2x will be the denominator. This 4e to the x will stay the same. And for the next one there, the e to the 3x will be at the bottom. So our derivative for our last question there, we have -4 over e to the 2x plus 4e to the x plus 3 over e to the 3x. Now, if you remember synonym mountain from a few lessons ago, we talked about the different words that we use for differentiation, and this is another one. So we're looking at the average rate of change for this function between x is 1 and x is 3. So we actually use a bit of a different process to find what this is. So you might remember for the average rate of change, we just have y2 take y1 over x2 take x1. So we don't actually have to use the differentiation process for this one. So all we're going to do is use a bit of substitution to find this. So the first thing we're going to do is find y when x equals 1 and then find y when x equals 3. So firstly, I'm substituting in x equals 3 into my rule. So I have 3 to the power of 3 plus 2 times 3. 3 to the power of 3 gives me 27 and 2 3s are 6. So we end up with 33. And lastly, I'm going to substitute in x equals 1. So I get 3 to the power of 1 plus 2 times 1. So I get 3 plus 2, which is 5. Now, all I need to do is put that into our rule that I wrote at the top there. So y2 is going to be 33 and y1 will be 5. So 33 take away 5. x2 is going to be 3 and x1 will be 1. So now we just need to solve. So 33 take away 5, that's going to give me 28. And 3 take away 1 is 2. So 28 divided by 2 is going to be 14. Now, it doesn't actually matter if we make 33y2 and 3x2. We could do it around the other way. So if we did that, 5 take 33 over 1 take away 3 is going to give us negative 28 over negative 2, which, surprise, surprise, is the exact same thing. The only thing you need to make sure is that we keep the correct pairs in the correct orders. So if we keep this as y2 and this as x2, that's fine. If we keep this as y2 and this as x2, that's completely fine. The only way you're going to make a mistake is if we accidentally swap them. So swapping our pairs that we find. And just to recap what we went over in this lesson, when we have e to the power of x, the derivative is going to be the exact same thing. So e to the power of x. But if we have something like e to the 2x, then the derivative is going to change just slightly. So we differentiate the power and bring that to the front. So we'll have a coefficient there of e. Looking at the graphs there of these two, we can see that the derivative graph is just slightly quicker, increases a little bit quicker because this 2 acts as a dilation factor. And again, our index laws should be second nature to you. So if they aren't at the moment, I would recommend practicing these. And what we'll be looking at in our next lesson is differentiating log e of x. In this video, we'll be looking at the derivative of the natural log graph. Now, we've got a picture here of the natural log, and I just wanted to show you what the derivative is doing before we get into any rules. So on the left-hand side down here, we can see that the graph is rapidly increasing. So our gradient is a very steep positive gradient there. And then as we go onto the right-hand side over here, it slowly declines. So it is still a positive gradient, however, it has gone a lot slower. So the gradient is sort of tending towards 0. So if I were to sketch the gradient graph of this one, so the derivative graph of this, we're actually going to start over here on the positive x-axis side. All right, we've got a rapid increase there, and then as we get to the right-hand side, it is slowly going down. So it is slowly decreasing there. So I have drawn the graph of the derivative there. Now, what kind of graph does this look like? If you had said the graph of y equals 1 over x, you would be correct. So we'll have a look at that shortly. In this lesson, we are looking at differentiating log e of x, so the natural log. So we'll be looking at two different things today. Firstly, just differentiating the natural log where we have kx in the middle there, and then differentiating log e of ax plus b. So as we saw in the first video there, we know that the derivative of the natural log there is 1 over x. And the way that we can prove that is on the right-hand side here. So y is 1 over x, the derivative of our natural log. So firstly, we need to recall the relationship that a natural log has with the exponentials. So we have this relationship here. Okay, so we have y equals log e to the x. We can rewrite that in exponential form as e to the power of y equals x. So we're going to use that to prove why 1 over x is the derivative. So we are going to rewrite our y equals log e of x as x equals e to the power of y. And then we can differentiate that now using what we learned in our last lesson on exponentials. If we differentiate x, we get dx dy equals e to the power of y. So it stays exactly the same. And from before, so from up here, we know that e to the y equals x. So we are going to replace e to the power of y with x there. And if we just do a simple reciprocal, we are going to find, so we're going to swap the dy and dx, flip that onto the top there, and we are going to flip our x as well to create a fraction. So flipping that up to the top, we get dy over dx, and then flipping our x, we get 1 over x. So now we have something a little bit different. We have a coefficient of x here within our log. And what the rule says is that the derivative of this here, log e to the kx, equals 1 over x still. So the reason for that being, we're going to use a chain rule to help us find why that works. So in order to prove why we have our derivative of log e to the kx equaling just 1 over x, on the right-hand side here, we've just set up the equation to prove it. So we have y equals log e to the kx. And what we're going to do is let u equal this part on the inside. So u equals kx. And then we're just going to rewrite y in terms of u. So we have y equals log e of u. So now we have two different equations. We've got u equals kx, and y equals log e of u, and we're going to differentiate those separately. So differentiating y with respect to u, we get 1 over u, which is what we saw on the previous video. And then differentiating u with respect to x, we get just k. Now, the next part of our chain rule says that we need to multiply those two derivatives together. So we get k times 1 over u. And then what we're going to do is just replace the u with our kx. So we end up getting k times 1 over kx. And then we can simply just cross out those k's there and simplify. And we end up with 1 over x. All right, our first worked example, we have find the derivative of the following with respect to x. So for A, we have f of x equals our natural log of 6x. Before we start, I just wanted to recall what we learned in the previous lesson about the chain rule. So if we have h of x equaling a function of g of x, so we've got a function within a function, then our derivative, so h prime x, is going to be, so then our derivative of h, we have h prime x is our derivative of f, so f prime, and then we have our g of x in the middle there, and then multiplied by the derivative of g of x. So just remembering this part here to help us with our little examples. So for our first example, we are going to separate this so that we can use our chain rule. We are going to let this 6x become a new function. So we have g of x equals 6x. And then we can rewrite f of x with g of x there. So now we can say that f of g of x is the log of g of x, and now we can differentiate those separately. So the derivative of g of x is just 6, and the derivative of f of g of x is 1 over g of x. So now when we are wanting to differentiate just f, we are going to multiply our two derivatives together. So our derivative of f of x, we get 6 multiplied by 1 over g of x, and then we substitute in our g of x there, which was 6x. So this part here, we end up getting 6 over 6x. We can cancel out those 6's there, and we end up getting 1 over x. So we know that the log of something like this is just going to be 1 over x, and then we just have the 3 at the front there. So we're just going to multiply those together to differentiate. So we get dy dx equals 3 times 1 over x. So we end up getting 3 over x as the derivative. Our next example has something a little bit different. We have 5x squared in that middle part there. So we're just going to see if that changes anything. So again, we are going to let f of x equal what's inside there. So let that equal 5x squared. And now we can rewrite g of x in terms of f of x. So now we have our two different functions. So now we can differentiate them separately. So when differentiating our g of f of x, we have our 2 multiplied by the derivative of this log here, which will just become 1 over f of x. So we've got 2 times 1 over f of x, so we have 2 over f of x. And now what we want to do is find the derivative of just g, so multiplying them both together. So we have our derivative of f of x there as 10x multiplied by our derivative of g of f of x. So that is the 2 over f of x. Multiplying them together and substituting back in f of x, so substituting back in the 5x squared there, we end up getting 20x over 5x squared. And now we can cancel some things out. So we have 20 divided by 5, so we get 4. And we have x divided by x squared, so we can cancel some of those things out and end up getting just x on the bottom. So as you can see, we ended up with 4 as the numerator there, which is actually the product of this 2 here and the 2 there as the square. So a quick rule is if we've got something in front of the log, we can multiply it by a power if we have a power. Now we're looking at something different again. So we're differentiating log e of ax plus b. So I'm going to show you why the derivative is what it is using the chain rule again. So again, we're going to separate this into two different equations. We're going to let u equal what's in the middle there, so the ax plus b, and then rewrite y in terms of u. So we've got y equals log e of u. So differentiating them separately, we get dy du equals 1 over u, which is what we know, and we get du dx equals a, so just the coefficient of x there is the derivative for us. So now when we are differentiating y, we have dy dx equals our two derivatives multiplied together, so a times 1 over u. We can now replace u with that ax plus b, which is what we substituted it for, and we get a over ax plus b. For our worked example, we have find the derivative for g of x equals log e of 2x plus 3. So we're going to go the long way. We're going to use the chain rule rather than using the quick way. So we are going to let f of x equal what's in the brackets there. So equals 2x plus 3. So now we can rewrite g of x in terms of f of x. So we have g of f of x equals log e of f of x. So now we have our two different equations. We are going to differentiate them separately. So differentiating f of x, we just have the coefficient there of x, so we just have 2. And differentiating g of f of x, we know that it's just 1 over whatever's in the bracket there, so 1 over f of x. And now differentiating g, we multiply them together. So the derivative of g of x, we get 2 times 1 over f of x. And now we can substitute back in f of x equals 2x plus 3. So we end up getting 2 over 2x plus 3. Before we move on to the next video on differentiating circular functions, I just wanted to highlight a quick tip. We had some feedback from the examiners from last year's exam, and one thing they have said to remind our students is that you need to make sure you keep the brackets in your logarithms and keep your vinculum, so the fraction line, straight or horizontal. There were a lot of mix-ups there and a lot of mistakes made without using brackets, and they found it very difficult to determine what their students were trying to say. So I've just written a quick little thing here for you. So if you're writing your fractions like this, it is not the same as 2x plus 1. So please make sure you keep your fraction line horizontal. In this lesson, I'll be introducing a new trigonometric identity that we'll need to use for differentiating circular functions. Luckily for those in methods, we don't have that many to remember. And what I mean by trigonometric identities is all the rules that you have learned when using circular functions, plus many, many more that I couldn't actually fit onto this screen. So count yourselves lucky. In this lesson, we are looking at differentiating circular functions. So in this lesson, we are looking at differentiating sine, then cosine, then looking at differentiating the tangent function. So firstly, differentiating sine is the nice and easy one. It's plain and simple. When we differentiate y equals sine of x, we get dy dx equals cos x. So they're just swapping there. If we have a k value in the middle there as a coefficient of x, that just comes to the front there, and it becomes k cos kx as the derivative. The reason why, just using the chain rule over here on the right-hand side. So if we have y equals sine of k theta, what we are going to do is let u equal what's in the middle there, so k theta, and then rewrite y in terms of u, so we get y equals sine of u. Now differentiating each of those separately, we get dy du equals cos u, and then du d theta equals just k, so just the part in front of the theta there. And then finding the derivative of y, we have dy dx equals the product of those two derivatives. So we have cos of u times k, and then we're just substituting what u was back into cos. So we have cos of k theta times k. So that is our answer there, k cos k theta. So to start this one off, what we're going to do is look at what's inside the bracket there and differentiate that. So we can see that the derivative of 4 theta is just going to be 4. And then I could say that u prime equals just 4. So the derivative of u is just 4. So from the rule that we learned in the previous video, we know that we are just going to multiply whatever our derivative is by the derivative of the inside. So since it is sine, it is going to go to cos. So the derivative of f theta is going to be 3 times cos and whatever was in the bracket there, so 4 theta, multiplied by the derivative of the inside of the bracket, so multiplied by 4. And we end up getting 12 cos 4 theta. For our next example, I'm not going to take the cheat way out. I'm going to do it the long way to show you how the derivative changes there. So what I can do is I can let the inside of the bracket there equal u. So I have let u equal theta squared take away 3 theta. And then I'm going to rewrite y in terms of u. So I have y equals negative sine u. So now I'm going to differentiate those separately. So for u, I get du d theta equals 2 theta take away 3. And then differentiating y with respect to u, so in terms of u, I have dy du equals negative cos of u. And now what we're going to do is multiply those two together to find the derivative of y. So to start with, I get dy d theta equals 2 theta take away 3, all multiplied by negative cos of u. And now I'm just going to substitute what u was back into the rule. All right, so I end up getting negative 1 multiplied by 2 theta take away 3, then multiplied by cos of theta squared take away 3 theta. And just to get rid of this negative here, this one there, I'm just going to apply that to the bracket at the front there. So multiplying everything in there by negative 1, I get 3 take away 2 theta multiplied by cos of theta squared take away 3 theta. For this example, we have find the derivative for g of theta equals sine squared, and then we have 2 theta cubed take away 5 theta in the bracket there. Now to make life easier, I'm just going to rearrange that so we can easily differentiate. So I can rewrite that as sine 2 theta cubed take away 5 theta and then all squared. So that is what this square is doing. It's just squaring the whole function there. So what I'm going to do now is let h equal what's inside the bracket there, and then I'm going to rewrite g in terms of h. So I end up getting g of h of theta equals h theta all squared. So what I can do now is differentiate each of those separately. So the derivative of h, we end up getting in brackets 6 times theta squared, take away 5. So the derivative of the inside there. So that 3 there comes to the front, multiplies by the 2, and then we take away 1 from that power. So that's how we get the 6 theta squared. And then we have the negative 5 theta. We just take the coefficient of theta. So we have negative 5. And then the derivative of sine, as we saw before, is just cos, and then whatever's in the bracket there. When we differentiate g with respect to h, we end up just getting 2 multiplied by h of theta. So the power there comes to the front, we take away 1 from the power, so we're just left with 1 at the top there for the power. So we're just going to ignore him. So what we do from here is we substitute back in what h of theta was. So we had our sine of 2 theta cubed take away 5 theta, and then we're just multiplying that by what is on the right-hand side here. So in order to simplify this here, I've got a 2 at the front here of sine, and then this at the front here of cos. So I can multiply those together, and I end up getting 12 theta squared take away 10, and then just multiplying that by the rest of the function. So we end up having 12 theta squared take away 10 multiplied by sine of 2 theta cubed take away 5 theta multiplied by cos of 2 theta cubed take away 5 theta. Moving on to differentiating cosine. Now, it's not as easy as differentiating sine, but still a little bit simple either way. When we differentiate cos, we end up getting the graph of negative sine x. And again, if we have something in the middle there, the derivative goes to the outside and multiplies by the function. So if we had cos of k of x, our derivative will be negative k sine k of x. Now, the reason why our derivative is going to be negative sine is because if we look at the graph over here, we can see what's happening to cos and then sketch our derivative graph. But I've already sketched it here for you. So let's look at what's happening for our graph of cos of x. So at the very start, we have our maximum point there, and then our gradient is decreasing. So you can see the gradient is decreasing all the way here until pi, where it becomes 0. And then the gradient starts to increase again, all the way to 2 pi. Now, if we look at our graph of our reflected sine graph, we have axis-intercepts there at 0, pi, and 2 pi. So now if we ignore that this is the y-axis and call it the gradient axis, so what is happening to the gradient at each point, we know that along the x-axis, the gradient is 0. So at each of our maximum points for cos, it is going through the x-axis for our negative sine graph. We can also see that from 0 to pi, we have negative gradient at the bottom there. So again, because our y-axis is our gradient, it's going to be below the x-axis. And then for cos, from pi to 2 pi, the gradient is positive, so it's increasing. So that is why our graph for sine is above the x-axis there. So hopefully that really helps you to remember why the derivative of cos is negative sine, so our reflected sine graph. So for our 2 examples, we are finding the derivative of each of them with respect to theta. Our first one, we have f of theta equals negative 3 cos 5 theta. So to start with, differentiating this one, we are going to keep that negative 3 at the front there and then multiply by the derivative of cos 5 theta. So we know that the derivative of cos becomes negative sine. So I've got the negative sign there. And then we have the 5 theta inside the bracket. And then we're going to multiply by the derivative of what's inside there. So the derivative of 5 theta just gives us 5. So simplifying all that, we have negative 3 and another negative and then times 5. So we have negative 3 times negative 5, which gives us 15 sine 5 theta. For our second example, we have y equals 3 cos 2 theta squared and then all squared. So again, to make life easier, I am just going to take what's on the inside there, so that cos 2 theta squared, and square that so that we know what is happening with that little square at the top there. So we end up getting y equals 3 times cos 2 theta squared all squared. So now what I can do is let u equal what's on the inside there. So I've got u equals cos 2 theta squared. And then I can rewrite y in terms of u. So I have just y equals 3u squared. And now I'm going to differentiate those separately. So differentiating u in terms of theta, we know that cos becomes negative sine. So I've got my negative sine there. And then I'm going to multiply by the derivative of what's on the inside here. So I've got 2 theta all squared. And then what happens is the square comes to the front there, multiplies by the 2, and then we have the theta. So that's why I've got the 4 theta there. So for the derivative of u, we have negative 4 theta sine and then 2 theta squared. Differentiating y with respect to u, we just have 6u. So the square comes to the front, multiplies by the 3, that's how we get the 6. And then taking away 1 from the power, we just get 1 anyway, so we end up with 6u. Putting that all together, we are going to multiply the two derivatives together. So we've got dy d theta equals dy du times du d theta. So we have our 6u multiplied by our negative 4 theta sine 2 theta squared. And then what I can do from here is just multiply the negative 4 and the 6. So I get the negative 24, and substituting back in what u equaled, which was the cos 2 theta squared. So that is where this cos 2 theta squared has come from. So finally, we get negative 24 cos 2 theta squared times sine 2 theta squared. Now we're looking at differentiating tan, and this is where the new identity is coming into it. So firstly, our key takeaway is if we have y equals tan of x, then our derivative is this here. So this is sec squared x. So if we have y equals tan of k of x, again, we're bringing that k to the front there. So we'll have k sec squared and then kx. So what is sec? Well, we have a relationship here that sec of theta or sec of x, whatever you're going to use, is 1 over cos of that variable. So in this case, we have 1 over cos of theta. So then when we have our square there, it's just going to be the same, but with a square. So we've got sec squared theta equals 1 over cos squared theta. So below we have the graph of y equals tan of x and y equals 1 over cos squared x. So blue is tan and red is our 1 over cos squared x, which is the same as our sec squared x. And what you can see for tan is it is actually constantly increasing. So our gradient is always positive. So that is why our red graph there, so the 1 over cos squared x, is always above the x-axis. So if we treat the red graph as the derivative graph and the y-axis as our derivative, then we are always going to be above the x-axis there. We can see at our almost inflection points for tan, it is getting close to 0 for the gradient. So our red graph here is getting closer to the x-axis, so it's sort of bottoming out a little bit as our gradient is slower. And then as we tend to the right-hand side for each of our tan graphs, it is starting to increase quite quickly, which is why our graph is increasing quickly as well, sort of matching that part there. So our first example, we have f of theta equaling tan 4 theta squared take away 5 theta. So firstly, we have our f prime theta, and then as we know, tan becomes sec squared when we differentiate. So I'm just going to rewrite what's inside the bracket and copy it down there. And now what I need to do is multiply by the derivative of what's inside that bracket there. So multiplying by the derivative of this part here. So I've got 4 theta squared take away 5 theta. So the square is going to multiply by the 4 at the front. So I'm going to have 8 theta. And then differentiating negative 5 theta, I just get negative 5. And just be careful that you make sure to keep those all in brackets as well. So we're multiplying by that whole part, not just the 8 theta out the front. And I'm just going to rewrite that so I have the 8 theta take away 5 at the front rather than at the back. For our next example, we have something a little bit different. So we actually have e to the power of tan 2 theta. So what we're going to do here is use the chain rule. So I'm going to let u equal tan 2 theta, and I'm going to let y equal e to the power of u. So I've got two different equations here now, so I can differentiate them separately. So differentiating u with respect to theta, I end up getting sec squared 2 theta multiplied by the derivative of the inside part there. So I'm just going to be multiplying by 2. And then differentiating y with respect to u, if we remember from a few lessons ago, the derivative of e to the power of x, or in this case u, is just going to be the exact same thing, so e to the power of u. So now when differentiating, we are just going to multiply the two derivatives together. Since this is just an expression and not an actual equation, I'm going to use some different notation. So we're going to have d theta, and then define our expression in the bracket there. And now we can multiply our two derivatives together. So we have e to the power of u multiplied by 2 sec squared 2 theta. What I can do now is multiply this by the e at the start there. So I get 2e, and then I'm going to replace u with what we changed it for, so the tan 2 theta. So we end up getting 2e to the power of tan 2 theta multiplied by sec squared of 2 theta. Another tricky one for you. So we have find the derivative of y equals log e of tan 2 theta. So firstly, before we start, I just want to remind you that if we have a log function there, so I've got y equals log e of f of x, then the derivative of that is just going to be the derivative of f of x divided by f of x. So we're going to use that to help us with this problem here. So firstly, I'm going to let u equal what's on the inside here. So u is going to be tan 2 theta, and then I'm going to rewrite y in terms of u. So I have y equals log e of u. Now I have two different equations, so I can differentiate them separately. So firstly, I have du d theta. That equals sec squared 2 theta, and then multiply by the derivative of the inside part there, which is just 2. So we get 2 sec squared 2 theta. Now differentiating y with respect to u, so using the rule that we have up the top there, we end up just getting 1 over u. So the derivative of u is just 1, so that's why we've got 1 as the numerator, and then u is the denominator. So using those, we're going to multiply them together to find the derivative of y. So multiplying those two together, we end up getting 2 sec squared of 2 theta divided by tan 2 theta. Now we could leave our answer like this, however there is another way that this answer could look. Now, you most likely won't have to do this, but I just wanted to show you how one equation can be represented in a different way. So firstly, just recalling that the relationship between tan, cos, and sine. So if we have tan of x, it is the same as sine over cos. So if we have the reciprocal 1 over tan 2 theta, then that is going to equal cos 2 theta over sine 2 theta. And as we saw previously, sec squared 2 theta is the same as 1 over cos squared 2 theta. So using those, we're going to change what our derivative looks like. So I'm just going to replace our tan 2 theta and our sec with the relationships that we can see above here. So we'll have 2 cos 2 theta over sine 2 theta. That's going to replace our tan at the bottom there, and then multiplying by our sec squared 2 theta, which is the 1 over cos squared 2 theta. And what we can see here is we've got a cos on the top, on the bottom, and they are both 2 theta as well, so we can cancel those out. So we end up getting 2 over sine 2 theta cos 2 theta. So in our summary page, we have the derivatives of all of our circular functions and just a recall of the different relationships. So we've got our tan theta and sec squared. And just a reminder that these are actually on your formula sheet. However, the exact values are not. So please make sure you are committing those to memory. So either remembering how to draw the triangles, or if you really are that keen, drawing out the table of exact values. But in our next video, we are looking at the product rule. So we'll see you then. We've previously looked at differentiating sums of functions, which were nice and easy and straightforward. So we're all sort of feeling like the people in the first picture, feeling happy that this calculus business is fine and dandy. In this lesson, we'll be looking at differentiating products of functions. So you'd think that you could just simply multiply the derivatives together using a bit of logic. However, and I'm sorry to burst your bubble, but it's a little bit more complex than that. In this lesson, we are looking at the product rule. So in this lesson, we are looking at the second point of our study design dot point there. So looking at derivatives of product of functions. So firstly, we're looking at the product rule, and then we're just looking at a different notation for our product rule. So as I said, the derivative of two functions multiplied together is a little bit trickier. So I'm going to step you through this. So if we have a function h of x, which is the product of f and g of x, then the derivative is given by this rule here. So what we have is we've got just f of x multiplied by the derivative of g, and then we have the derivative of f of x multiplied by just our function g. So we have some steps here to help you figure out the derivative when we are using the product rule. So the very first thing is we need to identify the two functions that we are multiplying together. And then we are going to find the derivative of each of these functions separately. And then what we're going to do is substitute those derivatives and our normal functions into this rule at the top here, and then simplify where necessary. So we've got an example on the right-hand side here, just to sort of get you into using the product rule. So we've got our function h of x equals x squared times sine 2x, and we need to identify our two functions. So I know that sine 2x is a function, and I know that x squared is a quadratic function. So we're going to separate those two and write two different equations. So we have f of x equals x squared and g of x equals sine 2x. Now we need to differentiate them separately. So differentiating x squared, we get 2x, and then differentiating sine, if you watch the last video, we would know that sine becomes cos when we differentiate, and then we need to multiply by the derivative of the inside there, so using the chain rule. So we get 2 cos 2x as our derivative for g. Now what we're going to do is substitute all of those values into this rule that we have on the left-hand side here. So we have the derivative of h equals our normal function for f, so x squared, multiplied by the derivative of g. So that's where we've got the 2 cos 2x. And then we're just adding our derivative of f and then multiplying by our normal function for u. So simplifying this one, we get 2x squared cos 2x plus 2x sine 2x. So hopefully the first example here is going to be nice and straightforward. So we have find the derivative of f of x equals 2x e to the power of 3x. So first step is identify our two different functions. So we've got one here for 2x, and then our second one is our exponential there, so e to the 3x. So what I'm going to do is I'm going to let g equal the first function and h equal the second function. And what I do now, so step 2 is differentiate each of them separately. So the derivative of g just becomes 2, and the derivative of h, we get 3e to the power of 3x. So now we're going to put all of that into our rule that I'm just going to put at the top here, actually, just so that we remember what that rule is. So putting all of this together, firstly, we are finding just g of x. So we've got 2x at the start, multiplied by the derivative for h. So we have our 3e to the power of 3x, and then we're going to add our h, which was the e to the power of 3x, multiplied by the derivative of g, which was 2. So simplifying all of that, we get 6x e to the power of 3x plus 2e to the power of 3x. For this worked example, we have identified the two functions for you, which is nice of us. So firstly, we have f of x equals sine 2x and g of x equals 5x to the power of 3. And our function h is just those two multiplied together. So finding the derivative for h, firstly, we need to find the derivative for f and for g. So differentiating f, we end up getting 2 times cos 2x. So we had the derivative of sine, we get cos, and then multiply by the derivative of the inside part there. So the 2x, the derivative of that is just 2. And then differentiating g, we get 15x squared. So for up here for g, we bring the 3 to the front, multiply by the 5. That's how we get the 15. And then we take away 1 from the power. So 3 take 1 is 2. That's how we get 15x squared. So putting that all together, we have the derivative of h equals f of x, so sine 2x, multiplied by the derivative of g, which is our 15x squared. And then adding g of x, which was our 5x cubed, multiplied by the derivative of f, so the 2 cos 2x. Simplifying that, we get 15x squared sine 2x, and then adding 10x cubed cos 2x. Now, if you accidentally reverse the order, so if you have our derivative for f over here, and then our derivative for g over here, it doesn't matter. That's okay, because we are just adding, so our order doesn't really matter here. However, in our next lesson, our order is definitely going to be very important. So here we're looking at the exact same thing, just a different notation. So this is if we have something like y equals uv, where u and v are functions of x. The derivative here is given by just our normal v multiplied by the derivative of u, and then adding u times our derivative of v. So we've got some similar steps here. So firstly, identify the two functions that you are multiplying together. Then our second step is writing your new equation for u and v separately, and then differentiate each of them separately. Next, you're going to substitute them into the rule that you were given up the top here, and then simplify where necessary. So we've got another example here on the right-hand side just to help you through this one. So we've got y equals e to the power of 3x and then multiplied by x to the power of 3, take away 2x squared plus 6. So our two functions that are being multiplied together is this one here and then this one here, our cubic. So what we do then is differentiate them separately. So the derivative of u here, so I let u equal that first function there and v equal the second one, and then differentiating them separately. So the derivative of u, we get 3e to the power of 3x, and then the derivative of v, we get 3x squared, take away 4x. So now putting it into the rule, we're going to do things a little bit backwards now, but we've got v first. So we've got just v multiplied by the derivative of u, and then we have u multiplied by the derivative of v. So simplifying all of that down, we can actually take out e to the power of 3x as a common factor. And then we have e to the power of 3x times 3x cubed, take 3x squared, take 4x plus 18. We have for y equals x times log e of 2x plus 1, find dy dx. So firstly, identify the two functions that are being multiplied together. So we've got x as the first one, and then all of this is the second one. So I'm going to let u equal x and v equal everything else. What I do now is differentiate them separately. So I have du dx, and the derivative of that is just 1. And the derivative of v, I'm going to get 2 over 2x plus 1. So if you're not sure how to do this, go back a couple of lessons when we differentiate log functions, and you'll be able to differentiate that nicely. So now differentiating y, I have dy dx, and I'm just going to substitute everything that I have into the rule at the top here. So we have our v function first, so the log e 2x plus 1, multiplied by the derivative of u, which was 1. And then we're adding just our u function, so just x, multiplied by the derivative of v, so the 2 over 2x plus 1. Now we're going to simplify. And all we had to do there is just multiply by 1 for the first function and by x for the second function. So we end up getting log e of 2x plus 1 plus 2x over 2x plus 1. For this example here, again, we are going to identify our two functions being multiplied together. So we are going to let u equal the e to the power of 2x, and let v equal the square root of 2x take away 3. Now I'm just going to rewrite what v is so that we can differentiate it nicely. So rather than having this square root sign, I'm just going to raise it to the power of a half, just to make everything nice and easy to work with. So differentiating u, I end up getting 2e to the power of 2x, and differentiating v, what I do is I bring that power to the front and multiply by what's in the bracket there, so 2 take away 3. I take away 1 from the power, so a half take away 1, I get a negative half, and then on the outside there, I'm multiplying by the derivative of the inside. So the derivative there is just 2, so just multiplying by 2. So simplifying that down, I get 2 times a half, which is just 1, and this negative power means that I'm going to create a fraction, so all of that is going to become the denominator, so I end up getting 1 over the square root of 2x take 3. So now we need to put everything together. So the derivative of y, we get just our normal v multiplied by the derivative of u. And then we have our normal u multiplied by the derivative of v. So we end up getting 2e to the power of 2x multiplied by the square root of 2x take 3 plus e to the power of 2x divided by the square root of 2x take 3. So we could leave our answer like this, or we could combine our two terms so that we just have one fraction. So the first step on the right-hand side here is multiplying our first term by square root of 2x take away 3 divided by square root of 2x take 3. So what that's going to do is just multiply out that square root. So we end up getting the 2x take away 3, and then that can all be divided by the square root of 2x take away 3. I've multiplied the 2 through the bracket there, so I end up getting 4x take away 6, so just multiplying by 2, and then leaving everything else as it is. The reason I've done that is because I have an e to the power of 2x over here on the left, and an e to the power of 2x on the right. So I'm going to combine them, take them out as a common factor. So I've done that in the next step here. I've got e to the power of 2x, and then in brackets I have my 4x take away 6, and then the plus 1, which came from the e to the power of 2x up the top there. Combining that, I end up getting e to the power of 2x, and then in brackets 4x take 5, all divided by that square root of 2x take away 3. Lastly, this formula is on your formula sheet, so you don't need to worry about memorizing it. Just make sure that you remember how to use it. In our next lesson, we are looking at the quotient rule, so we'll see you then. Let's recap what we've learned over the last few lessons. We can differentiate circular functions, logarithms, exponentials, polynomials, composite functions, and products of functions. But what about something like this? We've got f of x over g of x. So using what we already know about the index laws and the product rule, let's rewrite this into something that's workable. So if we rewrite this using negative indices, we get this here. H of x equals f of x times g of x to the power of -1. I've just brought that g of x up to the top there. Let's use the steps that we learned in our last lesson to differentiate something like this using our product rule. So firstly, we identify our two functions that we are multiplying together. So we have f of x and g of x to the power of -1 now. So I'm using u and v to introduce these. So I have u equals f of x and v equals our g of x to the power of -1. And you'll notice here that we are going to use the chain rule. So firstly, differentiating u, so I've just got u prime equals the derivative of f, so just f prime x. And the derivative of v, since we are using the chain rule, we bring the power to the front here, so we have our -1 at the front. We take away 1 from the power, so that's why we have the -2 there. And then we multiply by the derivative of the inside. So it's just g of x in the middle there, so our derivative is g prime x. What we do now is we put all of that information into our product rule that we learned in our last lesson. So at the top here, I've just used our v and u dash so that we know what's happening here. So firstly, the v was just the g of x to the power of -1, and our u prime was our f prime x, and then we are adding the opposite. So we're adding our u multiplied by our v prime. So we've got our f of x multiplied by v prime, which was the -1 times gx to the power of -2, and then multiplied by g of x. So we get something a bit yuck here, but we're going to simplify that to make it a little bit nicer. So what we can do with our negative indices is change them so that they are at the bottom of the fraction and become positive indices. So this first part here, we end up getting f prime x over g of x. And then our second part, again, we're going to flip it so that we have the negative indices become positive indices at the bottom of our fraction. So we have f of x times g prime x divided by g of x all squared. Now, if I want to combine these fractions, I need to multiply this first term by g of x over g of x. So that gives me f prime x times g of x, and then take away f of x times g prime x all over g of x to the power of 2. Now, this probably doesn't mean anything to you, but what we have just found is the quotient rule. Now, this probably doesn't mean much to you yet, but we have just found the quotient rule, which is what we'll be using in this lesson. In this lesson, we are looking at the quotient rule. In this lesson, we are looking at the quotient rule and then just an alternative notation for the quotient rule. So similar to what we did for the product rule, how we had our two different notations, that's what we're doing in this lesson. So as we saw at the start of this lesson, we have the quotient rule is given by this huge thing over here, okay? So like what we did with the product rule, we've got some steps here for you. So step 1 is just identify the numerator and the denominator. And then step 2 is just write a separate equation for each of those. The third step is to find the derivative of both of those equations separately and then substitute each expression into the rule that we've got at the top here. So I've got an example for you just to make things a little bit easier. So I've got h of x equals 3x squared over x plus 1. So we're writing our two different functions here, so two different equations. We've got f of x equals the numerator, so our 3x squared, and g of x is our denominator, so the x plus 1. Now we differentiate each of them separately. So our 3x squared, when we differentiate that, we get 6x. And when we differentiate x plus 1, we just get 1. And now we're going to put all of that information into the nice little formula that we have over here on the left. So the derivative of f goes first, multiplied by just our g. And then we take away the derivative of g multiplied by just our normal f. And then we divide all of that by g all squared. Our first example, we are finding the derivative of this function here. We have f of x equals x plus 1 over e to the power of 2x. So again, firstly, identifying your two different functions. So I'm going to let g of x equal the numerator and h of x equal the denominator. So to start with, I've just written the quotient rule at the top here, just as a point of reference for you. But what we need to do is write our two separate equations for our numerator and our denominator. So I've got g of x equals x plus 1 and h of x equals x to the power of 2x. Differentiating them separately, I get the derivative of g equals 1, and the derivative of h, I get 2e to the power of 2x. So now I'm going to put all of that information into our quotient rule over here on the right. So firstly, I have h of x multiplied by the derivative of g. and then I take away g multiplied by the derivative of h. Then I divide all of that by h squared. Simplifying that, so I have e to the power of 2x times 1, so just e to the power of 2x, and then I have the x plus 1 multiplied by the 2e to the power of 2x, and then dividing all of that by e to the power of 2x all squared, so when we square our indices, they just multiply the powers together, so I get e to the power of 4x down here. And now what I can do is divide through by e to the power of 2x, as that is common for each of those terms there. So doing that, I get 1 over here, so I've divided through by e to the power of 2x, leaves me with just 1. And then on the left-hand side, I've divided by the e to the power of 2x, leaving me just with that 2 times x plus 1. And what I can do now is expand those brackets and combine some terms. So I've expanded the brackets on the right there, so I have 1 take away 2x take away 2, and that's all divided by e to the power of 2x, which then leaves me with negative 2x take away 1 over e to the power of 2x. Okay, here we are finding the derivative of g of x equaling sine x over x squared. So again, we need to identify our two different functions and label them f of x and h of x. So after writing my two equations, so the f of x equaling sine x and h of x equaling x squared, I need to differentiate each of those separately. So when we differentiate sine, it becomes cos, and when we differentiate x squared, it becomes 2x. So putting that into our rule, we start off with h of x, so that is our x squared there, multiplied by the derivative of f, so that is our cos x there, and then we are going to take away our f of x, multiplied by our derivative of h of x. We are then dividing all of that by h of x squared, and then we're going to simplify. So we end up getting x squared times cos x take away 2x sine x divided by x to the power of 4. Again, because when we have indices to the power of another index, we are going to multiply those powers together. So that is how we get the x to the power of 4. From here, each of these terms have an x in them, so I'm going to divide through by just an x. So our first one is just going to become x cos x, and then we're going to get rid of that x in the second term there. So it just becomes negative 2 sine x, and then we have to get rid of an x down the bottom. So instead of x to the power of 4, it is x to the power of 3. So here's an alternative notation for you. So before we were looking at function notation with f of x and g of x, but here we're just using y, u, and v. So firstly, our numerator is just going to be u, and our denominator will be v. So then looking at the equation below, so our formula below, the derivative of y is given by just v multiplied by the derivative of u, take away u multiplied by the derivative of v, and then dividing by v all squared. So again, we've got an example for you and some steps there. So the steps are the same as the previous video, but the example here, we've got y equals 3x squared divided by sine of 2x. Again, separating both of those functions into different equations so that we have u equals 3x squared and v equals sine 2x. So now we differentiate them separately. So the derivative of u is going to be 6x, and the derivative of v, well, when we differentiate sine, we get cos, and then we need to multiply by the derivative of the inside of that bracket there. So we end up getting cos 2x multiplied by 2, so just 2 cos 2x. So now differentiating y, we put all of that information into the formula on the left-hand side there. So starting off with v, so the sine 2x multiplied by the derivative of u, so the 6x, and then we take away u multiplied by the derivative of v, and then we divide it by v all squared. So when we simplify that, we get 6x times sine 2x, take away 6x squared times cos 2x divided by sine 2x all squared as well. So using that different notation, we'll have a go at a worked example here. So we have y equals e to the power of 3x divided by sine x plus 1, and we need to find the derivative. So firstly, we're going to let u equal the numerator and v equal the denominator. So to start with, we let u equal e to the power of 3x and v equals sine x plus 1. Now we differentiate each of them separately. So differentiating u, we get 3e to the power of 3x, and differentiating v, we just get cos x. Now putting all of that into the quotient rule that we have seen, the very first thing that we have is just our v term multiplied by the derivative of u, and then we take away our u term multiplied by the derivative of v, and then divide that by v squared. So what I've done in the next step is simplified a little bit, but you'll also see that I've multiplied everything in the brackets here by 3. That is so that I can factor out this e to the power of 3x in the next step. So what I've done is I've taken that out as a common factor, so e to the power of 3x, and then left everything else inside the bracket. So that leaves me with the 3 sine x plus 3, and then take away the cos x on the right-hand side there. And then still dividing all of that by sine x plus 1 all squared. So just a reminder, these rules will be included on the formula sheet for your exam, so you don't need to worry about memorizing them. Just make sure you remember how to use them. And what is coming up next, we are looking at our chapter checks, so going through all of the skills that you have learned in Chapter 7 and applying them in tech-free and then tech-enabled questions.
Are we allowed to split dy and dx? There are many people who will tell you that splitting dy and dx will take you to the dark side of mathematics. And if you're a little bit uncomfortable with doing that, then you feel a discomfort that has been passed down from maths teacher to maths student for hundreds of years. But many people do make this split. Engineers and physicists do it regularly to get practical, real-world results. Some will tell you splitting dy and dx is not rigorous. If you get into the habit of splitting dy and dx, then when you end up in university and you study multivariable calculus and you don't understand what the dx and the dy means, you'll run into trouble. I say it's important to understand, yes, what it means. But if you deny yourself the intuition and the understanding that comes from treating dy and dx as their own entities, then you deny yourself the very understanding of calculus itself. So to those who say splitting dy and dx will take you to the dark side, I say, come to the dark side. Our two founders of calculus, Isaac Newton and Gottfried Wilhelm Leibniz. Leibniz was a master of notation, and he gave us the concept of dy and dx. To him, they were quantities that could be split and treated as their own infinitesimally small values. Isaac Newton struggled with this idea. In his early works, he had the little symbol O to represent a tiny infinitesimally small change in time. But as he went on, he didn't quite feel comfortable in the same way that you might not feel comfortable with the limit of something approaching an infinitely small value. Now, limits are actually rigorous, and they were the way that calculus was brought to rigor later on, but we'll get to them later. Newton, in his third addition to his work, De Quadratura Curvarum, he removed the little o from his notations, and he just worked with the ratios of these infinitely small values. He worked with fractions. That conflict that he felt represents the conflict that we find, and it's not a simple thing because for hundreds of years people didn't have a rigorous approach to calculus. They had to work with these infinitesimally small quantities, and our friend Bishop George Berkeley comes along and he says, hey, you scientists, what's going on? What's going on? What are these fractions? They are neither finite quantities nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? He said, you scientists criticize me for believing in God, but you believe just as wildly in these infinitely small values. So what's the deal, scientists? And this phrase, the ghosts of departed quantities, that notion troubled mathematicians for years to come. They troubled them in the same way that it troubled Newton and caused him to remove the O from his work. It didn't trouble Leibniz. He was like, this stuff works, the notation works, I'm gonna just keep rolling with it. But for mathematicians for hundreds of years were troubled by it, until we came to people like Cauchy and Weierstrass who developed a rigorous approach to calculus using limits. And so if you feel that conflict, it's because of this tension that's been passed down in mathematics for hundreds of years. People after Cauchy and Weierstrass, they threw out the idea of infinitesimals, this infinitely small value. They said, we're going to stick to limits, something very rigorous. And then in 1960, Abraham Robinson comes along. He gives us a rigorous basis for the idea of the hyperreals, which is not a common branch of maths, but it basically gives us suddenly rigor to work with these infinitesimally small quantities again. So you can see where the tension comes from. I argue that if you remove yourself, if you don't allow yourself to split dy and dx, then you actually don't allow yourself the understanding that came to Isaac Newton when he first grappled with calculus. You remove from yourself the understanding that Leibniz had when he made this notation and upon which we use a lot of our notation today. So come to the dark side. Embrace the idea of dy dx. It's going to give you a beautiful intuition for calculus. And I'm going to show you today how that intuition can lead to some pretty powerful ideas and hopefully explain a lot of the things about calculus that you've been doing, derivatives and product rules and all those kinds of things, but haven't quite yet been able to understand so far. So we're going to look at a 3-part series on the why of calculus. And today is going to be introducing this idea of infinitesimals, and we're going to use them to prove not a formal rigorous proof with limits, but an intuitive proof or an intuition for the common derivatives you've come across. In our next lesson, we're going to look at the product rule, we're going to look at the derivative of sine, and in our third lesson, we're going to look at why the antiderivative gives us the area. Now, I said that Newton and Leibniz were the founders of calculus, but really, as Newton said, he stands upon the shoulders of giants. The foundations of calculus began hundreds, if not thousands of years before, and we'll meet Archimedes at the beginning of our next lesson. Today we have 3 key ideas we're looking at. We're looking at the concept of this thing that is infinitely small. We're going to find an intuition for the derivative of x squared, and we're also going to find an intuition for the derivative of x cubed. We're going today to embrace the idea of something super small, something infinitely small, the infinitesimal. And there's different notation that we could use to approach this. We could use little Isaac Newton's letter O that he later threw away. We could use a more rigorous approach like a limit. Abraham Robinson, the guy who gave a rigorous approach to infinitesimals, introduced the concept of the hyperreals, numbers that aren't real numbers, but exist within and around them. So for example, let's take the numbers around 0, and we represent an infinitesimal with the symbol epsilon. And we say that little epsilon is smaller than any other real number. Now, it's not possible. You can't have a real number that's smaller than every other real number. We know you can always find something smaller than it. You can divide it by 2. But as a concept outside the real numbers, we can call this a hyperreal. And that allows us to then explore concepts of negative infinity and positive infinity and the sizes of things. And really, the crux of where a lot of this comes down to is whether you allow yourself to work with these numbers by themselves or whether you just allow yourself to work with them as ratios, right? You might say this tiny, infinitely small number by itself can't exist in the real numbers. But if I take 1, let's say double 1, and then I divide it by itself, then that is going to be a real number. And that sort of touches on the idea of why people like to keep dy and dx together. Because you might say, individually, there are these infinitely small values that aren't really real numbers and they don't really make much sense to me. But when I divide 2 tiny things together, if I divide 0.000002 by 0.000001, and imagine that there were infinitely many zeros there, even though that in itself, each number by itself is hard to grapple with, you could say together, they do produce a real number. And that's why some people do like to just stick with ratios. And Isaac Newton himself, when he got rid of the letter O, he went to stick with ratios. But today, we're going to break them apart. We're going to look at dx and dy as individual quantities, and we're going to use them to understand what's going on. I have those ideas summarized over here. There's one sort of point that I want to highlight for us, that I'd like us to think of dx as a tiny nudge in x, a tiny little push in x, and dy, because they are connected to each other, because we have a relationship between x and y, dy is the resulting tiny nudge in y. And if we think of it like that, it's going to be an excellent way to build an intuition for calculus. So answer this coming question, see what your understanding is so far, and then prepare yourselves, because we're about to do some very, very cool maths. Let's try and build an intuition for the derivative of x squared. And not just drop the power, times by the power, drop the power by 1. Let's feel it in our bones. We're going to model the idea of x squared as being the area of a square with length x. And then we could say the area here is x squared. So if we're trying to talk about a change in x squared, we could talk about a change in the area. How are we going to change this area? We're going to increase the side length of our square by a little nudge in x. So I'm going to nudge x to be a little bit bigger, an infinitely small amount, tiny, tiny nudge, okay? That's going to expand the square on a few sides over there and over there. And we'll also nudge it there. Remember, we're nudging the x by an amount, so it's going to nudge on the top the same as it does on the bottom. Can we now find an expression for the change in area, right? If dx is a tiny nudge in x, then dA is the resulting tiny nudge in A. What amount has been added on? Let's calculate it. We can actually look at these rectangles and we can say, hey, this one here has a height of dx and a length of x, and this one has a height of x and a length of dx. And so I can say that the tiny resulting nudge in area is going to equal x times dx, that's the first rectangle, plus x times dx. And then what about this tiny little square down here, this dx squared, right? That's going to be plus dx squared. I'm just checking something, guys. Now, hopefully that you can see that we have some common like terms here. We've got two lots of x, dx, plus dx squared. And you might see where this is going, this beautiful journey and adventure is going. Okay, well, I'll tell you where it's going. We're going to divide both sides by dx, and we're going to end up with this. dA dx is equal to 2x, which is the derivative of x squared. Mind blown. But to do that, we're going to have to deal with this dx squared. And there's a couple of ways to do it, right? Some people talk about orders of magnitude. They say, okay, maybe if I extend x by a tiny amount, I get a tiny thin rectangle that has an infinitely small width. It's basically no width at all. It's almost a line, but it's got a tiny width, so I'm prepared to say that rectangle has area. And I'm prepared to say that rectangle has area. But that little tiny box in the corner, it's infinitely small on both sides. It can't have area. I'm going to just let it go. And this is the beauty of maths, right? With limits, you can define a way that disappears, right? This is what Bishop Berkeley called the ghosts of departed quantities. Newton in his early works just let these things go. And if you feel a bit uncomfortable with that, you're like, well, that's the reason why we move towards the idea of limits. Or you could say, let me divide both sides by dx, and I get 2x plus a single dx. And now the ratio of two infinitely small values, that's a real number, and that's a real number. This is still in hyperreal land, and it's so small. It's so small compared to everything else, we just let it go. So there's two ways of letting it go. One is by getting rid of it here as the area of that little square. It's nothing. Or by saying, once we're back in real number land, this dx is insignificant compared to the rest. Either way, we're going to let it go, and we're going to arrive at this conclusion. The nudge in area divided by the nudge in the x value actually is 2x. And we know that the area was x squared, so that's the same thing as saying dx of x squared is equal to 2x. I've just shown you why the derivative of x squared is 2x. And it is one of the most beautiful things in the world. That idea is summarized over here if you'd like to consult it again in the future. Now, I'm going to give a series of multiple choice questions throughout this 3-part series that allow you to practically feel the concepts that I'm talking about. Let's have a look at the first question. Let's take the same approach and use it to build an intuition for the derivative of x cubed. And we're going to model x cubed as the volume of a cube with side lengths x. So to explore the derivative here, we're going to have to look at the resulting tiny change or tiny nudge in volume that comes from doing a tiny nudge in that value x. So let's try and do that. Let's try and nudge x a little bit along. So if we were to increase x by a little amount, dx, now I know I've got a gap between my item and the box, but that's just easy to see it. Really, it's pressed up right against the box. If we nudge x by a little bit, suddenly we add an extra page, an extra plane to the side of the box. And that's also going to happen to the front and to the top of the box as well. So hopefully you can see that we've actually added 3 blocks or 3 really thin, almost pages. What are they? Rectangular prisms to each dimension of the box as we extended x in a different direction. What's the new volume from each of these shapes? Well, if we just take the one on the right, we've got dx there. Its length along the bottom is x, and then the height going up is also x. So we can say that the resulting change in volume from a little shift in x is going to be 1x times dx. And there's actually 3 of them, because there's one on the side, there's one on the front, there's one on the top. That's not all. Like, if this was just what we wanted, we're already there. But if you're really good at visualizing what's going on here, you'll notice that the tiny extra nudge in volume we've had is more than just what we've written. If it was just that, it would be great. We could divide both sides by dx, would have dv dx equals 3x squared. done dilly done done. But there are a few other things involved as well. Right, if we've increased our x by the same amount in all directions, the new shape is a cube as well, and we can't have that gap between the two little planes that we've just made. It doesn't just exist on the top, it exists along the side and down the front as well. What's the volume of this rod that we've just added in? Well, along the bottom, it's got a base of dx, and its height is x. So we also have this rod, which is x dx squared. And how many? There are 3 of them. But if you've been paying even really close attention, you'll notice there's an extra shape as well. We have a little box left over at the top. And what's the volume of that tiny box? Well, that's going to be dx all cubed. And just to differentiate and show that I'm not doing the d of x squared. Now, by the same logic as in the previous example, these values are going to go away. Talking about a volume, we're prepared to say, yeah, the volume is going to extend by a tiny amount if you extend in one dimension. Like these rods, what's their base length and width? The length and the width is infinitely small. It's basically just a thin line, and a thin line has no volume. And that little box, it's not even a line, it's a point in space. It's got a width, length, and height, all of dx. No way does that have any volume, right? So we could just say these are the ghosts of departed quantities. They disappear and run away. Or if we wanted to, we could define a more sort of rigorous approach, and we could divide all sides by dx, and we'd get dv dx is equal to 3x squared plus 3x dx plus dx squared. And we can say, yeah, the ratio of 2 infinitely small values, that's a real number. That's a good thing. But basically in the same logic as limits, right, as dx approaches 0, this one and this one is going to disappear. And we're left with dv dx is 3x squared, and v is the same as x cubed, so the derivative of x cubed with respect to x is 3x squared. We have these ideas summarized over here along with this diagram. This cube was extended in a slightly different way. It was extended outwards that way, sideways this way, and up there. But the extension in all directions was a little dx, and the principles are the same as well. Here's a question coming up to help you get a practical feel of how this works with real numbers. So those are the key ideas summarized over here. In the remaining 2 lessons of this little Y of calculus series, we're going to continue thinking in this way. We're going to think of dx as a little nudge in x and dy as the resultant nudge in y. We've got a summary of where, or an intuition for the derivative of x squared and x cubed. I'll see you next time. We'll look at some more cool intuitions. One, we'll look at the product rule and try and get a sense of where that comes from. And we'll also look at the derivative of sine of theta as well. We're in the middle of a 3-part series journeying and exploring the Y of calculus. And the general theme throughout this 3-part series is that we're taking our classic dy dx and we are treating our dx and dy as individual related ideas. D theta is a little nudge in theta, and d sine theta is the resulting nudge in sine of theta. And that understanding, although not fully rigorous and it doesn't use limits, it does give us a beautiful intuition for many of the ideas behind calculus. In maths and in maths methods, we make a habit as teachers of often explaining from first principles where all these ideas come from. But I think the things that you have in front of you are actually 2 concepts that almost no one ever explains, right? With the intuitions that we established and built upon in the first of this 3-part series, I'm today going to give you an intuition as to why the product rule is the product rule and why the derivative of sine is cos. The history of calculus crosses millennia and continents. In its story, we see feuds, genius, religious bans, and documents lost for thousands of years. The history of calculus moves beyond mathematics and dives into the very nature of knowledge and truth itself. And we explored a little bit of that in the last lesson when we brought up Bishop Berkeley's attack of the idea of the infinitely small quantities. But today, let's raise the idea of those documents lost for thousands of years. People often make the mistake of saying or thinking that calculus was just brought into existence by Newton and Leibniz, and they argued who did it. But calculus has its underpinnings hundreds, if not thousands of years beforehand. People like Cavalieri, just in the few hundred years prior to Newton and Leibniz were developing these ideas, and they built their knowledge on the generation before them and the generation before them. The idea of infinitely small quantities was around for hundreds of years. It was Newton and Leibniz who formalized, who brought us the fundamental theorem of calculus, the interaction between the derivative and area, and spread it in the world to be used by engineers, by builders and thinkers and mathematicians and machine learning specialists in our modern day. But the story of calculus is a continuous cycle. It was built upon then. Newton said, "I stand upon the shoulders of giants." And Leibniz himself said, "He who understands Archimedes and Apollonius will admire less the achievements of the foremost men of later times." And if the person credited with developing calculus says that, then we can really accept that ourselves. Archimedes was around 200 years BC. And this is a document of his that was lost for thousands of years. It's called the Archimedes palimpsest. During some sacking or pillaging of a city in Greece, the document was stolen. And eventually, many, many years later, it was found and it was sent to a monastery in Palestine. And there were monks in the monastery who didn't necessarily set so much store by Archimedes' work. I don't know if they knew it was his or not. And then around 1229, they sort of wrote over it. They put some religious texts there. Anyway, years and years later, around 1840, 1906, I think some more work was done, the document was discovered. And behind the writings of the religious texts, someone could find the early works of Archimedes, the early works of this wonderful document that recorded some of the very first thoughts and ideas around calculus. What we're really doing in our journey of infinitesimals, our journey into examining dy and dx as these individual but related quantities, is we're taking ourselves back to the understandings of calculus from a few hundred years ago. And although it's not the same rigorous approach that we use today with limits, it does give us a deep intuition, an understanding, and a perspective on the way the early mathematicians thought about it. We all stand upon the shoulders of giants, and I think it's also worth me recognizing now and saying thank you to Grant Sanderson from 3 Blue 1 Brown, who first exposed me to some of these ideas that you're seeing in these lessons. He is absolutely incredible. I recommend you to go and watch him. And I hope you guys can take these ideas and one day teach them to some people as well. We're looking at the why of calculus, and we're looking at some more cool intuitions around the product rule and the derivative of sine of theta. 1 and 2. Let's remind ourselves what the product rule is looking at. We're trying to find the derivative of two functions of x, u of x times v of x. And we're saying, I want the derivative of this with respect to x. And there's some fancy rule that we get, u v dash v u dash plus in between, that sort of gives it to us. But we often just plug and play, and we don't really have a sense of why. Think back to our last lesson. We modeled the derivative of x squared as a square with side lengths of x. And so perhaps we could model the derivative of the product of something also with the idea of area. And that's what we're going to do. We're going to draw not a square, but a rectangle. And I'm going to make up some functions just to help us get a sense of what's going on. Let's say that we have u as being cos of x, and we have v as being x cubed. Now, of course, being functions of x, the cos and the x cubed are going to change. As x changes, the lengths of this rectangle are going to change. And so they don't necessarily change in the same way as each other. One might get bigger faster than the other one. They're both basically dependent on any changes in x. But we can still sort of say that whatever they do change to, the multiplication of them will still be the area of a rectangle. Let's think about what happens if we increase x by a little amount. We give it a nudge, okay? If we were to nudge x, that's going to result in a nudge to x cubed. And then this side of the rectangle is going to get bigger. It's going to be a nudge of x cubed that came from a nudge in x. And the same thing we can do to the other side. We can model over here. We can say if we nudge x, that could increase our cos as well. And the size of that increase is going to be a nudge in cos, right? A nudge in cos that came from that nudge in x. And we have a tiny little square here that has its own area too. We can write an expression for the new area. The change in the area, okay, instead of, we'll come back and we'll remind ourselves that the area is really just u times v. The nudge in a is going to be the added area to this rectangle. And let's look at this one first. The width or the length of that rectangle is cos of x, and its height is that nudge, that change to x cubed. We can then look at this rod over here. Well, it's not really a rod, it's just a flat piece of paper really. We're only in 2 dimensions. And we can say that the resulting area there is x cubed multiplied by the nudge that occurred to cos. And then we have the tiny square left over, which is d cos of x times d of x cubed. Okay? And just like in the previous lesson, we can sort of consider this in a few ways. We can say that square, if it's infinitely tall and infinitely small in height and infinitely small in width, it's really just a dot, right? I've zoomed in and made these things as big as possible to try and get a sense of them geometrically, but really that's so small, it's got a dot, right? That sort of rod on the bottom, the dx cubed cos x rod, that's its height it's basically just a straight line, right? And we kind of say, yeah, maybe if that line was had a little bit of oomph to it, then there's a bit of area there. But if there's an oomph up and an oomph to the side and they're so oomphy small, that's basically gone. So we could just cross off this term over here. That's what a lot of the mathematicians in the back in the day did. In the next step, we're going to divide both sides by dx. Well, I'm going to do it first, and we'll talk a little bit about what happened. And we're getting an expression that looks very, very close to our product rule. Now, could we just bring in dx from nowhere? Well, in some ways we could, but I want to sort of give you the sense that it's really logical to actually bring in x, because the change that happened to x cubed and the change that happened to cos x didn't just happen arbitrarily. They came from a change to dx. X moved a little bit. They were both functions of x, and then they both moved in their own way in relation to x, but they kind of still related to each other. So it makes a lot of sense to actually talk about d cos x in relation to dx and d x cubed in relation to dx. They're ratios that mean the same thing. The dx over here is the same as the dx over here. And so it really works to actually do this division. Now we get to this point and we say, what happens to this last term? Well, you could sort of think of it as maybe a really small number, 0.00001, times another really small number, 0.00002, divided by some other really small number, 0.003. And let's say maybe these two cancel out to be a non-small number, but when you multiply it by another really small number, perhaps it's going to disappear. Right? There's a few ways to play with that. You could work with limits and you could see what happens as this thing runs down to 0. Or you can just use the previous line and say, hey, the area of that little rectangle was insignificant, and that term is gone. What we're left over with is something absolutely amazing. dA is the same as duv dx. Cos is u. dx cubed dx is v dash. X cubed is v, and d cos x dx is u dash. And we have the product rule. uv dash plus vu dash. And we've summarized what's going on over here. Here we have the shapes to be quite large, but remember those d values are infinitely small. We've got a question coming up to help you practice and get a feel of how this looks if we work with some real numbers. Let's see if we can find the derivative of sine of theta. We'll take just the knowledge we have so far, this idea of working with infinitesimals, the idea of the derivative of sine of theta being the resultant tiny nudge in that sine of theta. When I nudged theta by a little bit, I'm going to push theta a little bit, and I'm going to see how much sine of theta changes. The derivative will be given by their relationship to each other. And the closest I've ever really seen someone do in methods classes around proving that the derivative of sine is cos is basically drawing the graphs. And you could say if you drew a derivative graph, then the slopes match it. The slope becomes the y values, and basically they look the same. But still feels a bit hand-wavy, because who's to say that the other function perfectly describes the slope of the original graph? It's not a bad approach, but let's see if we can, with only the knowledge we've done so far, pretend we're a few hundred years back and no one has discovered the derivative of sine. All we have is our understanding of these infinitely small changes, these little nudges, and our understanding of trigonometry. And we'll see whether we can find this derivative. How are we going to go about it? Let's go to the unit circle. Okay, that's where a lot of our ideas of sine and cos come from, right? Go to the unit circle, and we remind ourselves that the radius of the unit circle is 1, and if we draw a point at an angle of theta, we get cos of theta and sine of theta as that coordinate. Remember that from the unit circle with trig? The key idea here is that the sine of theta gives us the y value. I'll just write this at the top, y equals sine of theta. We're trying to find the change in sine of theta. Another way to say that is to say what's the change in the y value when I nudge theta by a little bit. So let's do that nudge of theta. I'm going to draw it a bit big, but in reality, we're really just nudging it an infinitely small amount. We've pushed theta up by d theta. And we say to ourselves, hey, what's the resulting change in the y value? Right? If I can calculate the resulting change in the y value, I found the resulting change in sine of theta. So how could we now try and work out that shift in y values? Perhaps we could use some ideas of geometry and trigonometry and angles. So I'm going to draw a right angle triangle whose height is the change in y. Now you might come along and say, hang on, that's not a triangle. The hypotenuse there is a curve. It's not a straight line. But go with me on this. As that d theta gets smaller and smaller, as it approaches 0, that curved line is going to look very, very close to a straight line. And I don't have the ability here to pinch with my fingers and zoom in, but if you were to make d theta super small and to really zoom in on that curve between the two points, it's going to look really, really close to a straight line. And it's very much a similar idea to what we do when we talk about integration. You know how we talk about integration as the area of the rectangles under the curve, right? And you say, well, hang on, there's a little bit of an error there. There's a bit of an error above the rectangle. It's not quite the area under the curve. But if you make those rectangles super, super thin, then as they get thinner and thinner and thinner, those errors to the curve disappear. And therefore the area of the rectangles is the area under the curve. We can say the same kind of thing here. As we get closer and closer, as that d theta gets super small, that basically becomes a straight line. So let's use that information, and let's try and work out a few things. Okay, I'm going to draw a dotted line over here, and using alternate angles from Year 10 maths, we can say if there's a theta over here, theta is going to have to exist there as well. And the other thing is that as d theta gets really small, in this little corner here, we're going to have a right angle, right? That's going to get closer and closer to a right angle. That's from the curve down to the blue line. That means that this little angle on the inside of the triangle is going to be 90 minus theta. And that makes this angle up the top theta as well, okay? So we're now starting to build the tools that we need to find this dy, this height of this triangle. Let's give a name to the hypotenuse. I'm just going to call it, I'll call it P for hypotenuse now. And we're going to say that cos of theta is equal to the adjacent, which is the change in y, divided by P. Now, how can we find the length of that hypotenuse? There's a formula to find the arc length of a circle. It's not covered in math methods, but it's covered in other maths. What you could say is that the circumference of a circle is 2 pi times its radius. And if you want only a portion of the entire curved length around it, you could just take the fraction of that part that you want. So what fraction of a circle do I want? I want the angle, the d theta, out of 360 degrees, out of 2 pi radians. So that's another way of saying that if I have a circle here, just to sort of give you a brief idea, and I said that's 30 degrees, then the arc length here is going to be 30 degrees out of 360 degrees times 2 pi r. Does that make sense? That the length of that arc is the same ratio to 2 pi r as the angle is to 360. That's sort of a different branch of maths, and if you're not sure about it, just take my word for it. This is the formula for the arc length of a circle. Hopefully you got a bit of an understanding of where that comes from. But basically, we've just found out that the value of P is going to be the angle for that arc out of 2 pi times 2 pi r. And that 2 pi cancels. And the radius of this circle is a unit circle, so the r is equal to 1. And therefore we have that P equals d theta. So we have cos of theta is dy d theta, or in other words, if y is sine of theta, d sine theta d theta equals cos of theta. It's pretty incredible. Just by nudging theta a bit, applying some geometry, finding what the resultant nudge in y is, we've found an understanding for the derivative of sine of theta. It blows my mind. So those are the key ideas today. We looked at an intuition for the product rule and also an understanding of why the derivative of sine is cos. We'll see a next lesson for the question that is always on students' minds and never properly gets answered. Why does the antiderivative give us area? The third part in our Why of Calculus series. And here we're going deep. We're going fundamental. We're looking at the fundamental theorem of calculus. A lot of people don't see this as a theorem. They just see this as like a notation trick, right? If I'm doing the integral from a to b, then antiderivative, chuck in b, chuck in a, minus them. Why is this considered the fundamental theorem of calculus? Because it summarizes the notion that the area is given by the antiderivative. Imagine that you didn't know that this notation here actually was the antiderivative, and you just saw it as the representation of area. Suddenly if someone comes along and says, hey, the area equals the antiderivative of b minus antiderivative of a, you'd be like, oh my God, that's a crazy statement. That's a crazy statement. That's a fundamental statement in calculus. And that was one of the great discoveries or great understandings that were brought to us around the time of Leibniz and Newton. And we're going to look at today why this is the case. I, for myself, wondered years and years why this was the case. It was never explained to me, and I tried to research and understand and just proved a little bit here and there. Hopefully, I'm going to give you that understanding today. Why does the reverse of the derivative give us area? One of the key ideas that I've been emphasizing during this three-part series is that calculus wasn't brought out of nothing by Leibniz and Newton, right? Calculus and the ideas of calculus existed for hundreds, in fact, thousands of years beforehand. And to demonstrate that idea, I've got here a text from the 1300s. This is 300 to 400 years before the time of Newton and Leibniz, by a dude called Oresme. And you can see that Oresme, even back then, was trying to find the area of things by breaking it up into small quantity. And the ideas of the indivisibles were around for a decent period of time before our two mates. This text is De Latitudinius Formarum, and there are other texts by Oresme as well. The tradition of calculus has been passed down from teacher to student for hundreds, not thousands of years. So let us together read it together and bring the wonder to life. Omnis rationalis opinio de velocitiae montum ponit in sequi aliquam proportionem, hec quidem proportionem excessus potentiae motoris and resististumente su potentiam remote. We're looking at the why of calculus. We're looking at antiderivatives and area. We're going to try and answer that elusive question. Why does the antiderivative give us area? It's one idea. We're going to try and explore it today. I want to approach the left-hand side of the fundamental theorem of calculus. This part over here. The right-hand side was f of b minus f of a, right? But I want to try and approach the left-hand side as though we don't yet know that the antiderivative is area. We just approach this left-hand side as the area between a and b, right, under the curve of x. And I'm going to try and show you why this notation is used to represent that idea. Okay, let's draw a little bit of a curve. You might have seen this sort of before. We're going to go from a to b, and we're going to look at a little rectangle over here, a little thin rectangle. And we're going to say that the width of this rectangle is dx. It's an infinitely small amount of x, a small little shift in x. Well, the height of that rectangle would be f of x, the height. So if you want the area of the rectangle, you'd have f of x. You'd multiply it by dx. And if you wanted the area under the curve, you would add up all the rectangles from the beginning of the region you're looking at to the end of the region. Now this little integral symbol is kind of like the letter S, meaning sum. And that's the idea. We're actually adding the areas of all those rectangles, and we're doing it from A to B. So hopefully that gives you a bit of understanding of where this notation comes from and why we use this notation to represent area. Now, I haven't told you why this is going to be calculated through the antiderivative, but I want you to sort of go along the process with me. Our first assumption is nothing to do with derivatives and antiderivatives. It's simply, I have an expression that represents the sum of all the rectangles. It represents the area under the curve. And I've summarized that idea in that note below. To show this idea of why the antiderivative gives us area, we're going to have to lay down some ground rules and agree to what we're actually looking for. Let me draw a bit of a graph just to sort of establish what the symbols are going to mean, and then we'll sort of go from there. We have a curve, f of x, and I'm going to say the area under the curve is represented by some function area of x. In other words, if x is over here, a of x will be the area. Well, I'm trying to just establish the rules, two rules or two expressions for things that are connected, right? A of x is the area under the graph up until the point x, and f of x is the graph itself. And our goal here is to say that the antiderivative of f of x gives area. Another way of formulating that is to reverse the process. Now, antiderivative, what does the word mean? It means the reverse of the derivative. So if the antiderivative of f is area, then the derivative of area has to be f, right? That's an equivalent statement. It's an equivalent statement to saying the derivative of area is f of x. Is that cool? That's sort of the ground rule I want us to work from, because if I can show you that the derivative of area, this area here, gives me the function, that's the same thing as saying the antiderivative of f gives area. Because that's all we do when we anti-differentiate. We say we have this idea of differentiation. We know its rates of change. It's like the gradient of the tangent to the graph at a point. But someone just comes along and say, hey, can you reverse that process? If you reverse that process, what do you get? Well, you get an antiderivative. And so we're going to try and tackle this from something that we do know. If we can show that the rate of change of area is the function itself, then we've achieved our goal. So let's try and go about doing this. We have here a curve, f of x. And I'm going to say that I've got the area up until the point x, right? I could write a of x, that's totally fine. It's the area under the curve to the point x. I might just write a for now just to sort of keep the notation a bit simple. And I'm going to come along and just like in our previous lessons where we increased the sizes of rectangles or squares or cubes or the angle of theta by a little tiny amount, I'm going to increase my x by a tiny amount as well. And I'm going to ask myself, what is the resultant change to the area? How much have I nudged the area by when I've nudged the little x by a certain amount, right? This new strip is going to have an area of the nudge that we've made, like the extra area that we've made. And we can try and get an expression for this, and try and get an expression for the change in area in terms of the change in x. And we can say the resultant nudge in area is going to equal the function, right? The height of that rectangle times by the nudge in x. Hopefully you can see that if we divide both sides by dx, we have that dA dx is equal to the function. In other words, we have that statement that I established on the previous slide. The derivative of area is the function itself. It's pretty cool. That's all you need. I'm going to, in the next slide and in later things, just go through a bit more detail. I'll try and show it to you a little bit with limits as well. But if you've got that idea, you've got it yourself. And hopefully this is intuitive, right? The rate of change of area under a curve has to be dependent. It has to be dependent on the height of the curve. If your curve is super, super tall, when you nudge a little bit to your x, your area is going to change more. It's going to change a lot, right? A lot, meaning a lot compared to if the graph was really low down. I'm laughing at myself by saying a lot because the actual change to area with a tiny nudge is still tiny, tiny, tiny. But everything's relative here, right? If your graph is super tall, then the resultant change to your area is going to be big, right? If your graph is super low, if f of x is low, then the resultant change to your area is going to be small. And so the rate of change of area with respect to x, right? Seeing derivatives as the rate of change, it is the height of the graph itself. It is the function. This is mind-blowingly simply beautiful, right? The most beautiful explanations are the simplest ones. And that means that we can reverse the process. That means that if we take the antiderivative of the function, we get the area, right? And if you wanted to, you could sort of say that by here, you could integrate both sides and you'd get area equals the antiderivative of f of x dx. That's sort of like a rough, I won't write it down fully because we need notation. We need A's and B's and a whole bunch of things. But that's the idea that we're working towards. So we're just summarizing that down here. The rate of change of area is the function. and therefore the antiderivative of the function will give us the area. I'm going to establish this a little bit more formally for those people who want to see something that involves some limits. Right? We're going to still have the same idea. We have a function, f of x, and let's say that the area under the curve to the point x is a of x, okay? And someone comes along and says, I want to increase the x by a tiny amount. Let's increase x by a value of h, okay? And someone comes along and says, hey, what is the area under the curve to the increased point? So previously, we had the area of x was this sort of blue section over here. And someone comes along and says, hey, I'd like to have the area all the way to the new value, to x plus h. What is the area under the curve from 0 to the point a of x plus h? And you could express that. We could say that's approximately equal to the previous area plus h times the height of the rectangle, f of x. Right? Looks pretty good. That's pretty fair. There's no hand-wavy things going on here. The area to the new value is approximately equal to the previous area plus h times f of x. We can take away a of x from both sides and we can divide by h, and we'll get a of x plus h minus a of x over h is approximately equal to f of x. Okay, now that's an approximation. There's no weird calculus assumptions happening here just yet. It's just a true statement that these things are approximately equal. Now, we can tell that this statement is going to get truer and truer the smaller h gets, right? Just like when with derivatives, if you want to find the gradient of the line between those 2 points and you say the gap between them is h, and we sort of do the limit as h approaches 0 of what's going on there, of the rise over the run, y2 minus y1 over x2 minus x1, we say that thing is going to become true as we take the limit as h approaches 0. We're going to do the same thing over here. We're going to say, let's let h approach 0. And as h approaches 0, this statement here is going to become not just approximately equal, but actually perfectly true. So let's do this. F of x is going to be equal. This statement will be equal when we take the limit as h approaches 0 of this expression. Now, I don't know about you, but this thing over here looks awfully familiar. Awfully familiar. That is the expression for the derivative of the function over here. And so what I've just shown you is that the f of x is equal to the derivative of the area. And that idea is the same thing we wrote on the previous slide. We said dA dx is the function itself. What we've just seen here is a bit of a more formal proof that shows that the function itself is the rate of change of the area. We've basically done it. We've shown that the rate of change of area under a curve is equal to the function itself, right? The rate of change of area is equal to the function itself. But I want to take this a little bit further forward and really hone in and arrive at the fundamental theorem of calculus that shows that the area between a and b is equal to the antiderivative at b minus the antiderivative at a. And to do that, let's remind ourselves how we defined this area function above. When I described it above, I said that's the area under the curve from 0 to x. So let's run with it. Let's now look at a curve, a different curve. We'll still call it f of x just for the notation's sake. And we're going to say I want the area from a to b. Now this a function I defined above, which we use to arrive at this understanding here, dA dx, is going to be the area from 0 to the x value. So if I want the area under here, I'll say that that's going to be this a function at a. And if I want the area from the beginning to b, then that's going to be, the entire purple thing is going to be the area of b. And hopefully you can see that if I want the area between a and b, I'm going to have to do a of b minus a of a. That is the area between a and b. Now, I haven't brought in any ideas of integration or anti-differentiation. I haven't brought in any ideas of anti-differentiation just yet. I've just expressed that I have this idea, this function a of x. And if you want to use that function to work out the area between a and b, you're going to set it up like this, a of b minus a of a. And I said that gives me the area. And so if we use this notation as we did at the beginning of the lesson, we say this is just the notation for the area. Again, I haven't brought in any of the ideas of differentiation and integration just yet. I just said area is this function at b minus this function at a. Then this statement that I've written for you is a pretty good statement. Right? We established that the function of a is the antiderivative of f. If you reverse the differentiation process on f, you get back a. And so this is the same thing as the antiderivative or an antiderivative of f at b minus the same antiderivative of f at a. And that's why we have the fundamental theorem of calculus. That's why the area from a to b is the same as the antiderivative at b minus the antiderivative at a. Now, when I defined a of x, I said the starting point was x equals 0, and I did that because that's convenient. It was a bit arbitrary. I could have used the starting point at x equals -1. As long as I chose a point that was sort of to the left of a and b, that's the best way to make this process convenient and easy to understand, then basically we would get the same results anyway. I just chose 0 as a way to sort of center our workings and make it easy to follow. Now, f of b by itself doesn't represent the area from 0 to b, just because when you take an antiderivative, you get a plus c. And here you get a plus c, but because there's a minus, it would be a minus c. And that c kind of represents the idea I just said, that I could have started the left point of this a of x function at 0 or a -1 or a -100. Wherever I would have started it, in the end, when I do one area minus the other area, it doesn't matter how far to the left you go, when you subtract them, you're always left over with just the section in between. So I just want to emphasize that idea that f of b by itself, it has a plus c in it. It doesn't necessarily mean the area from 0 to that point, but whatever your starting point is, when you subtract the two, you'll always end up with that orange area on the left. The c's, the area that's sort of left over to the left, is going to cancel out. And we're going to be left with the actual area between a and b. And that's pretty cool. That basically summarizes one of the most powerful ideas that came up around the time of Newton and Leibniz, that if we reverse the process of differentiation, we get the area under the curve. And that brings us to the end of the lesson. We've looked at the notation around the integral sign, why the integral from a to b f of x dx actually symbolically represents area. We've then explored the idea of the rate of change of area, and we've shown the rate of change of area is the function itself. And therefore, the integral or the antiderivative of the function gives us back the area. And then we expanded that idea to show the beauty behind the fundamental theorem of calculus, that the area under a curve from a to b is equal to the antiderivative at b minus the antiderivative at a. And that brings us to the end of this 3-part series, a journey into the why of calculus. We haven't been fully rigorous using limits all the time. We've taken an intuitive approach to our little dx's, our little da's, our little dy's. But hopefully it's given you a taste of how some of the great mathematicians thought about these ideas hundreds and hundreds of years ago, and even moving forward into the modern day. And hopefully it's given you an intuitive toolkit that you can use when you come across calculus ideas in the future.